All right, so let's get started going over this June 2017 Chemistry Regents. For those that want to continue listening from every question from 1 through 50, we can continue on. There's going to be a link to the free response section at the end of this. Also, if you want to just jump to the questions you've got wrong, if you've taken this test and now just want to review the wrong answers, please look below in the descriptions. I have the time code for every question. So let's be crazy and start in order and go to number 1. All right, so number 1 maybe. We have the following question. So number 1, which statement describes the structure of an atom? Now you should know the development of the atom came from a solid sphere to a model where we had a kind of solid sphere with electrons kind of embedded like plum pudding, because we discovered electrons by the J.J. Thomson cathode ray experiment. So these electrons are negative and they were embedded just haphazardly inside and outside of the atom, and the positive was all the way through. Then from the Rutherford experiment, the Ernest Rutherford experiment, the very famous gold foil, which basically discovered the nucleus of the atom, where all the mass of the atom was in this nucleus that was positive, okay, and the electrons are somehow outside of it. That's basically where we are. Now Bohr, if you remember, said that these electrons went in circular orbits and had distinct energy levels. So we went from that model to a Bohr model. We had this positive nucleus, and then we had these electron shells where electrons that existed far away from the nucleus, okay, had higher energy, and these were circular orbits. All right, and then we went to the current model of the atom, the quantum mechanical model, where we still have this positive nucleus where neutrons and protons exist, of course neutrons being neutral and having the same mass as protons, and then electrons existed, okay, in distinct areas with high probability, and they call these areas orbitals. Now, if you took a more advanced, okay, chemistry class, you learn that these orbitals, okay, the first one is an S is circular, and then there's of course another orbital, and these all depended upon, again, distance and proximity, but they had different shapes, but they're based upon the idea that electrons existed in these regions of space with high probabilities, and these electrons of course acted as waves. So that's a little breakdown of how this worked. But the bottom line is the nucleus, once we discovered it by the Ernest Rutherford gold foil, okay, the nucleus was positively charged. So that's something you needed to know from that. And of course, it's surrounded by the negatively charged electrons. Now, what could also help you in this area, especially if questions are talking about the size of charge, the differences of charge, and the mass, is table O. It's a very underutilized table for many students in chemistry, and we've used it for nuclear chemistry, but you should really use it for atomic. Let's go to table O and just review that. So here we are in table O, or as I like to say, table O, okay? And if you don't know, you go to table O for particles. And look at these particles here. The top number is, of course, the mass number. So the mass number is this top particle. And the bottom number is the charge, kind of like how many protons you have. Look at the proton. Has a mass number of 1, has a charge of +1. Now, they don't put it out here, but a beta particle is really an electron. So what do you have is you have a mass of 0, but you should know better. Even though putting a mass of 0, it's 2,000 times lighter than a proton or a neutron. So they put a 0, but it really has some mass and has a charge of -1. Okay, so important that you've got that there. Okay, notice that a proton has a mass of 1, and so does a neutron. So neutrons and protons. Notice a neutron has a 0 charge. That's why it's neutral. Okay, protons are positive. So the 3 subatomic particles are listed here with mass and charge if you had to compare them. Did you need this for this question? Well, if you forgot that electrons are negatively charged, okay, maybe. But again, a good place to go to table O in this area. So back to question 1. All right, so we've got a nucleus that's positive because of the protons that are in the nucleus and surrounded by negatively charged electrons, choice 3. So 1 is 3. Number 2, Which term is defined as the region in an atom where an electron is most likely located? So this question is really asking you, do you know the current model of the atom? So if you didn't have me go over question 1 with you, real quickly, the first model of the atom was a solid sphere. The second was the plum pudding model, where electrons are haphazardly kind of placed in a gel of positive nucleus, or at least a positive atom. The positive was kind of smeared throughout. Then we discovered that electrons, we discovered the nucleus in the Rutherford gold foil experiment was positive and small, and all the mass of the atom was in that small area. Then the Bohr model started organizing electrons and electron shells, and then the current quantum mechanical model was that these electrons acted in as waves. Okay, it was a duality of waves and particle behavior, but they can act as waves. That's a new thing. And that where the electrons are were based upon probability, and the region of space where they're found with the most probability is called an orbital. And that, we think, was given because it gave credit to the organization that Bohr said that electrons had based upon energy level, although he said it was based upon certainly just distances, and electrons travel in circular orbits. He was right that electrons existed in different energy levels. So orbit, and they add the AL, okay, for the current model. So that's where you get the word orbital. Orbit is the older version, the Bohr model, okay, where electrons existed in circular orbits. We found that that's not true. They don't go in circular paths, but they are organized based upon energy. So the current model, the quantum mechanical model, is what this question was saying. Did you know the quantum mechanical model? And the quantum mechanical model, again, based upon electrons, can exist as waves and particles. Electrons exist in regions of space called orbitals based on probability. That's important. Moving on to question 3. So number 2 is 2, and now number 3. Number 3, what is the number of electrons in an atom of scandium? So my people, I teach my kids, anytime you hear atom, you say neutral. So if we're at a really cool chemistry dance party, I say atom, you say neutral. Atom, you say neutral. Atom, you say neutral. Atom. Okay, so anytime you hear atom, you know to say neutral, which means an atom is always going to have a charge of 0. And we know in the nucleus we have protons that are positive, and we know on the outside there are electrons that are equally, okay, have the same size, magnitude of charge, but negative charge. So protons are positive 1, electrons are negative 1. So if an atom is neutral and all the positive comes from protons and all the electrons are negatively charged, then we should know that the proton number has to equal the electron number. Hey, so all we've got to do is go find scandium on our periodic table, and then go find that proton number. It has to equal the electron numbers because protons and electrons have the same magnitude of charge, just differences. So protons have to equal electrons. Let's go to the periodic table. So here we are at the periodic table of elements, and all we need to know is the proton number for scandium, and it'll equal the electron number. But our problem is you may not know what scandium is because you have these what? Okay, we have these elemental symbols that represent boron, carbon. Which one's scandium? Is that scandium? Okay, so what we do, if you don't know, another underutilized table is table S that gives you the element's symbol for its name. Let's go there. And here we are, table S gives you a bunch of different things: electronegativity, melting point, boiling point, density, atomic radius, first ionization energy. But in this case, we just need the symbol for scandium. So I go look, and there I find my scandium, scandalous, right? And there it's SC, and it's atomic number 21. Actually, I don't have to go back to the periodic table anymore, because if it's atomic number 21, we know that every single element has a unique atomic number, and the atomic number equals the protons, right? Every single element has a unique number of protons, which the protons have to equal the electrons. So scandium has 21 protons, and if it is an atom, hopefully you said neutral, okay, it has 21 electrons. So back to our question. So 21 electrons. Okay, now, just so we understand, okay, when you find scandium on the periodic table, they're going to write the 21 below. So the 21 below is right here. That's the proton number. It's atomic number. But this top number is the mass number, and often people want you to, they love to have a distractor. A distractor is a choice that looks appealing and people take it. So people will see this number and say, hey, that must be at 45. But this is the atomic mass. This is the what? Protons plus the neutrons. Since neutrons and protons have the same mass, table O tells you that. So that's how we get through that. Now, of course, you should also know that this is the weighted average of all the isotopes as well. So the most abundant isotope is scandium-45, but we're after this atomic number, which is the proton number, which equals the electrons. Okay, so 31 is choice 1, 21. On to number 4. Which particle has the least mass? Okay, now we've got protons, electrons, helium atoms, hydrogen atoms. All right, now I'm going to make some space over here because I can, and we'll make these guys reappear later. But particles, how can I know this? Well, you're never going to memorize stuff like this, so it's a place to look. And as I've talked about earlier in the first part of this question, table O is your friend. In table O, a proton is written like this: hydrogen with a 1 and a 1. An electron, which is really a beta particle in table O. So that's one way to keep, if you want to have information that you know is handy, a beta particle in table O is written like this: e to the 0 to the negative 1. A helium atom, okay, we written with He, atomic number 2, and that'd be given to me in our reference table with a mass of 4. And then a hydrogen atom, okay, would be written like this. Okay, notice the proton and the hydrogen atom are written very similarly. Now, a hydrogen atom, we should know, is 1 proton at 1 positive with 1 electron. Okay, this proton written in table O is just written like this because a proton has a mass of 1 and a atomic number of 1. So the one that has the least mass is the one that's going to have the top number that's the smallest. So clearly in this case, electron, which in table O is a what? Beta particle. Okay, if you've never been to table O and haven't reviewed the other questions, let's go back there. But the one with the smallest mass, now don't fall in love with the think that electron is 0 from table O. Okay, it is 2,000 times lighter than a proton. Now protons are tiny. Okay, not that funny though, but protons are tiny. So if I have the mass of an electron, if it's 2,000 times smaller than a proton, which is tiny, its mass is really insignificant. So they put the 0 here. And by the way, as you're going to see, they call this an alpha particle. Notice it's 2 protons, 2 positives, and then 4 minus 2 is 2 neutrons. I'll write them as N's. And since a neutron and a proton have the same mass, that's the heaviest particle. Now they said a helium atom, which really means that this is going to have 2 electrons. But you'll see that as well. All right, and so if I adding electrons, that really is not going to change the mass. The mass of the atom, okay, is due to the neutrons and protons. But let's go back to table O to show you that. So the answer, okay, is an electron, which is a beta particle. And again, where to look for this would be table O. Let's take a gander. So in table O, what do we have here? The beta particle. Okay, it's really an electron. Really helpful to see it as electrons and look at its nuclear equation, we call here. 0 for the mass, top number is mass, and the charge is -1. Okay, notice the alpha particle I mentioned is a helium nucleus. You have to add 2 electrons, but it's a mass of 4. Okay, and this is the charge of 2. Now we always think the atomic number is 2. So how do you have a negative atomic number? Hey, it's the opposite charge, opposite thing of a proton, which would be an electron. Notice a neutron has a mass of 1. Notice a proton, a mass of 1. Notice a neutron has no charge, hey, and a proton has a mass of 1. So you can see that neutrons and protons have the same mass. The entire mass of an atom is protons and neutrons. Again, this could be very helpful in these types of equations or these types of questions where you forget about the mass of certain particles. So the lightest particle from table O is, of course, the electron, the beta particle. So number 4 is definitely 2, that very light electron that has mass. We put 0 there because it's really, really tiny, but there is some mass. Okay, number 5. Which electron transition in an excited atom results in a release of energy? All right, so now we're getting back or getting onto the idea that the atom has some arrangement of energy levels. So for those that weren't with me in the earlier questions, I talked about the Bohr model, which had a positive nucleus, that's the positive, but then it had these orbits, these circular paths that electrons were arranged. Now that's what Bohr described them as. He was incorrect that electrons went in circular orbits, but he was right that they existed in certain energy levels. And the electrons that existed farther away were in these higher energy orbits. So we're going to use that analogy here, okay? So the key here is excited. So let me just get some area here. Let's wipe this out. We'll bring these guys back later when we do these questions if you need to. And let's do this. Okay, so I've got a positive nucleus due to the protons. There's neutrons in here, but they don't have a charge, but the entire nuclear charge is due to the protons. Okay, and now we're going to have circular orbits. Now I know electrons do not go in these circular orbits, but we can think of these as shells, and we can use this as an analogy. And what do we know? We know that this would be the first, the second, and the third, and we'll put out the fourth shell. And well, we're going to pretend that shells are circular orbits. We can do that because, hey, it's based on proximity, how far away from the nucleus we are. So now, the key here is that if I've got electrons that are closer to the nucleus, I write E negative 1 is for an electron. I've been doing it since the beginning of this video, and that's what we do here. So here's my electron. Now, it's pretty close to this nucleus. So it feels the nucleus really, really a lot. Great scientific word. There's a high coulombic attraction, if you want to sound fancy. Electrostatic attraction between this negative and these positives are very, very strong. So electron, because it's close to the nucleus, feels the nucleus more. And we say that this shell, okay, has lower energy. Lower E, energy. Don't confuse that for electron. Because it just doesn't have an ability to do much because it's so close to the positive nucleus. Now, electrons that can exist out here on the fourth energy level are farther away from the nucleus. And therefore, because of that distance, they feel the nucleus less. And because of that, they have higher energy. Another thing you should be aware of, okay, is that things that have lower energy are said to be stable. Stable means low energy. It's a word we use throughout this course. Things do not change their state if they have low energy. You need a lot of energy to change their state. Things with high energy, okay, are unstable. With the high energy, they're going to do something with that high energy at some point. And we say things that are unstable, at least for electrons, hey, they're excited. Now, how do we get to an excited state? Because that's the point here I underline. Somehow, okay, if I want an excited atom, hey, excited, I have high energy, okay, and I want to release that energy. Well, there's only two ways I can go. I could jump to a higher energy level, but wait a minute. If I have to jump away, which we know the farther I jump away, this could be the fifth energy level, right? If I want to jump to the fifth or jump farther away, guess what? I would need more energy because in this position, I feel the what? Nucleus less. So this is the even this position electron would need to have higher energy to overcome this positive nucleus. So to jump away requires more energy. Like, look at here. If you didn't like my explanation, this guy is so close. For him to jump to the fourth, from the first to the fourth, he would require a lot of energy to overcome this. Now, this one would require not as much, but still would require some energy, because in the position of the fourth shell, okay, he is still closer than the position of the fifth shell. So to get to the fifth shell, easy for me to say, he would need to absorb energy. So if I want to release energy, and that's what this question is, I must be going from a state of high energy to low energy. So therefore, party people, this must be a leap backwards. Okay? So a release of energy would mean you're going to go to a place that's more stable and low energy. And if you go from high energy to low energy, you release it. In fact, you should know that release of energy in the form of spectra, or photons of light, that we can use to identify spectra, okay, that we can identify different atoms based on their unique energy levels. So jumping farther away to overcome this positive pulling force of the nucleus, we would need energy, and to jump back to my ground state or lower energy state close to the nucleus, I'd have to lose that extra energy. So if you don't like any of that, which choice is different? First shell to the third, I'm going away. That would be an absorption of energy. Second shell to the fourth shell, that's going away. It's an absorption of energy. Third shell to the fourth shell, going away. So the only choice there that's going backwards and going from a high energy state to a low energy state is choice 4. Fourth to the second, going back to a ground state, going back to a more stable state, you have to release energy. And that energy, although not part of the question, it's part of a lot of other questions, is released in the form of photons of light. So 5 is 4. Moving on to 6. Number 6. On the periodic table, the number of protons of an atom, of an element, is indicated by its what? Okay, if you have no clue how to do this, let's go to the periodic table to show you where the hints are. And voila, here we are, the periodic table, the one you'll have for the test. Now, in the key area, we have some things here. Selected oxidation states, the relative atomic masses are based on carbon-12, okay? But more importantly, look at this number here. The biggest and boldest number in a periodic table is the atomic number. And if you look carefully at all the other atoms, they all have unique atomic numbers, which means that every single different element is made up of a unique number of protons. Now you said, how do I know that bottom number is a proton? Well, you should know that atoms are based upon proton numbers. Also in table O, okay, you'll see hydrogen 1 over 1, and this is equal to a proton. So this bottom number 1 is a proton. Okay, why does it has a number 1 here? Because it has a mass of 1. Okay, so that's what we do there. So back to the question. So the atom of an element indicated, the number of protons of an atom of an element is indicated by its atomic number. Number 2, the biggest number. Carbon has a 6. Hydrogen has a 1. Every element. The top numbers are mass numbers. Okay, they include the protons plus the neutrons. Notice carbon would have 6 neutrons, 12 minus 6, because a proton and a neutron have the same mass. Notice hydrogen 1 would have 0 neutrons, 1 minus 1. They get the neutrons, we can subtract. Okay, number 7. Number 7, which type of formula shows an element symbol for each atom and a line for a bond between each atoms? Okay, very weird kind of question, but what they're after is the following. So let's say I have something called ethane, which by the way is given to you in table Q. Ethane has 2 carbons, single bonds, and then it has these other bonds for the hydrogens that I'll put out. And so this is a Lewis dot diagram. You could also consider it a Lewis dot diagram. Okay, don't forget if you had lone pairs, you'd have to show that. but this is C2H6. And we would call, okay, a formula that shows this type of arrangement a structural formula. And why a structural formula? It's showing the structural, okay? Off with the R there. Okay, so the structural formula is there, and this would be a molecular formula. And why do we care about the structure? We care about the structure because structure is king, okay, especially in organic chemistry. You change the structure, you change the function. Form and function you learn in biology. You change the actual shape of an enzyme, you change its ability to catalyze reactions, its ability to do its things. You also learn in more advanced chemistry classes if something is branched and has a different shape, its type of attractive forces will be different as well, and its boiling points and melting points, those physical properties will be different as well. Okay, so very important. So this is a structural formula. Now, let's talk about something that I didn't talk about. Let's talk about one of the choices here that's a distractor, empirical. Now, I said molecular is C2H6. And it's kind of the same as the empirical. Let me show you the difference. The molecular is exactly how a molecule actually bonds itself. Okay, so this is a molecule. Now, how do I know it's a molecule? It's made up of nonmetals, carbon, hydrogen. These guys are above the staircase, up to the right. Now, hydrogen, of course, is listed over to the left and above the first row of metals, but it's not a metal. I always call it the Waldo. They put it over there, but it's really a small atom, pretty highly electronegative, unlike the other atoms in group 1. It's not a group 1 metal at all, but they put it there because of one valence electron. But this is a nonmetal, so is carbon, and they want to share electrons because they attract electrons so strongly they're forced to share them. So this is the exact shape of this particle we call a molecule. Okay, now all things that bond covalently, nonmetals, make molecules. So the exact number of carbons and hydrogens in this case is its molecular formula. Now, if we were to try to come up with this in lab, a lot of times we'd come up with the lowest ratio because we would find the mass ratio of carbon to hydrogen in a lab because you really can't count carbons and hydrogens in a microscope. So we do kind of laboratory procedures where we can come up with the percentage. And what we'd come up is we'd come up with CH3 in lab oftentimes. If you notice, this is the lowest ratio, and that's what an empirical formula is. So even though that's not a good choice, I want to review that there. The empirical is the lowest ratio of my molecular. And then sometimes moleculars are also empirical. We know water exists as one oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons. And then we have hydrogen, who has one valence electron. And you notice by sharing 2 more electrons, 1 apiece to the hydrogen, this oxygen is sharing 8, which feels like its octet. This feels like it's sharing 2. They don't become ionic compounds because they both have high attractions for electrons. They're nonmetals. Okay, so this is the particle. Okay, and hydrogen feels like it has 2 electrons like helium. Oxygen feels like it has 8 electrons like its noble gas in its row. Okay, so this is the exact molecular formula, but hello, H2O is the lowest ratio already. So this is how it exists, and it's its lowest ratio. So here's an example where water, H2O, can be both a molecular and empirical. All right, and that's just something to review there because you will see that. So number 7 is 2. Let's go on to number 8. Number 8, what is conserved in all chemical reactions? Now, chemical reactions are dealing with changes of electrons somehow. Somehow we're either going to gain or lose or just kind of move charges around. But they deal with the electrons always. Nuclear chemistry has nothing to do with electrons. But in any case, what's conserved? Okay, let's take a reaction given in table I. Let's take sodium chloride, and let's make that A a little bit smaller. Okay, little Na. I shouldn't have 2 capitals there. And so let's do that again and get that A smaller, right? So NaCl, sodium chloride. This is an ionization reaction. They write water over the arrow to show that we do this in water, and it becomes Na plus, aqueous, which means it makes a homogeneous solution. It dissolves with water, plus Cl negative, and that's also aqueous. They dissolves completely, okay? And from table F, all group 1 ions are soluble, so this dissolves. Now, what's conserved? Number one, mass is conserved. You have 1 sodium, you still have 1 sodium. We have 1 chlorine, and we still have 1 chlorine, okay? So very important that mass is definitely conserved, but we don't see that in our choices, all right? Also, energy is conserved, meaning we don't create or destroy energy, just like we don't create sodium out of the blue. The reason why we know that the mass is always conserved, we balance. Now in this case we don't have to balance because we have 1 sodium for 1 sodium, 1 chlorine for 1 chlorine. Okay, so they're very important to understand that the mass is we balance because of the conservation of mass. Now there is energy associated with this reaction. We write the energy, it's an endothermic reaction, so it'd be on the reactant side, but who doesn't care? It doesn't really matter. That energy is not created out of blue, it's converted from one form to the other. So energy and mass are both what? Conserved. Now, what people forget is also charge is conserved. Notice there's a charge total of 0 on this side. Why? Because a +1 and a -1 makes 0. Or, hey, there's no charges written for sodium chloride. So this is a compound. And all compounds, just like all atoms, neutral, okay, are neutral. They're zeros. So on this side of the reactant side, we have a total charge of 0. On the product side, we've got a +1 and we've got a -1. If you add them together, hello, that's going to be 0 too. Doesn't mean that all reactions will balance out to have 0 on both sides, but it does mean that the charge is conserved. Okay, and if something else to think about, if we had copper, okay, +1, gaining an electron, which we call reduction, this is our half reactions, become copper 0, and then we had zinc by itself becoming zinc +2, it would have to give off 2 electrons. Okay, and this is oxidation, losing electrons is Leo. This is gaining electrons, reduction, right? Gaining electrons. Electrons would be adding to the copper. Now notice something in this half reaction, as you probably have learned, we have to balance the electrons. Why? Because we have to balance the charge. We're giving off 2 electrons here. We're only absorbing 1 here. So what we do is we multiply this side by 2, if you remember. That gives me 2 electrons. And now we can see that 2 electrons are being what? Absorbed, and 2 are given off. And now the charge is balanced, and now the reaction is balanced. We balance the charge, we automatically balance the reaction. And the overall reaction would be 2 copper +1 plus zinc, that's an atom, neutral, okay, goes to 2 coppers, 0, neutral, plus zinc +2. I'm running out of space. Look at the total charge on this side. Hello, 2 times +1 is +2. All right, so this side is +2. The zinc 0 is 0. 2 times 0 is still 0, and then you got a zinc +2. Notice +2 on both sides. Charge is conserved. Okay, so that's really important you get that. But if you know, one thing you want to get down is mass, okay, energy, and charge. And so atoms are not created nor destroyed. Energy is not created nor destroyed. And electrons are not created nor destroyed. So that means they're just interchanged. And you have to have the same number on one side as the other to show that. So they're after the charge here. They didn't have mass or energy, but you could have had the other two somewhere. I've seen that. Okay, so number 9 is next. Number 9. In which type of reaction can two compounds exchange ions to form two different compounds, two different formulas? All right, well, what would synthesis be? Well, synthesis would be that we're going to make something from its elements. So here's synthesis. Let's say hydrogen plus oxygen is going to make water, which is H2O. Now I have to balance this because of law of conservation of mass. I have 2 H's already and 1 O. Okay, so I'm gonna, to get 2 oxygens, I put a coefficient here, and of course that's going to be 4 H's, and I'd put a 2 here. But this is synthesis. We're going to make one thing. Decomposition would be the exact opposite. If I take two H2Os and by itself it breaks down into its elemental forms, this is decomposition, decomposing. Single replacement would be like the reaction I just did for number 8, where I had, let's say, like zinc plus copper chloride. And notice this is 0, this is -1, this is +2. And what's going to happen is the zinc's going to replace the copper and make zinc chloride and then pure copper. This is an example of a redox reaction, and I can identify redox reactions by having something that's a 0. And by the way, this was a redox reaction because these guys are elements. They have zeros as well. So everything I just drew here are redox reactions. And I say this because you can get a question in part 2 where they say, hey, what kind of reaction is this? And you're like, oh, I forget what synthesis or decomposition is. And all you'd have to say in part 2 is say, hey, these are all redox. And how do I identify a redox reaction? Well, you could do oxidation states and see if they change. This is 0, this is 0, this is +1, this is -2. Because when oxidation numbers are changing, it's because electrons are being passed around. Or you can just identify a 0, which is just a standalone element. Okay, atoms. Okay, here's an atom, neutral. Okay, and anytime you have an atom, neutral, or an element, diatomic or not, they have to be a 0 when they're by themselves, and they will not be 0 when they're bonded to something else. So essentially, by the order of elimination, process of elimination, 4 is the answer. Now, what would be double replacement? Because you need to be able to identify and also do this. Well, what if I had zinc, okay, nitrate? This is a polyatomic ion, NO3, plus, let's make it Ki, and we're going to basically, the zinc is +2, and K is +1. The ones in front are positive. Nitrate's -1 based on table E, iodines are -1, and all we're going to do is what? This positive go with this negative. We're going to basically do-si-do if you're into square dancing. We're just going to switch partners. So zinc goes to the iodine. Now, so zinc is still +2. Iodine's -1, so we need 2 of them. And then this K plus, it's going to go in front, goes with this negative. And since K is +1, and nitrates collectively, that polyatomic ion is -1, it goes like that. Okay, you don't write the charges. I'm just showing you that this is zinc +2 here. It's still +2 here. That's why it's not a redox reaction, because number 1, you don't see a what? Standalone element, either what? Diatomic or monoatomic. So there's no zeros. And all of these ion charges are staying the same. You're just switching partners. Now, of course, when you write this reaction, you wouldn't write the charges. I'm just kind of teaching you here. And of course, I didn't balance. This should be a 2 here, my bad. 2 nitrates. Okay, because each nitrate's -1. All right, and so I would need a 2 here for the 2 nitrates, 2 Ks. I'd throw a 2 there and there. All right, so in any case, that is a double replacement reaction. It's not a redox. I'm just switching the positive and negatives. And if you notice something, one little trick here is when you have polyatomic ions, keep them together when you balance. But in any case, that's not really part of the question, but we're reviewing these types of reactions. And of course, number 9 is 4. Number 10. So number 10, a really interesting question. At STP, standard temperature and pressure, table A of your reference table, if you didn't know what these values are, but they're not really changing the problem here. We're just saying that we have 2 5-gram solid samples of different ionic compounds, which means they have different chemical formulas. Okay, but they happen to have the same density. Now, density is a physical property that we can basically use to identify different compounds. But in this case, they have the same compound. I'm sorry, they have different compounds, but they have the same density. So these solid samples could be differentiated. Now, differentiated means you could identify one from the other. So if you got stuck on that word, I totally get it. But differentiated means you can separate them based upon differences. By their what? Well, density, of course, and if you needed this, it's in table T of your reference table, mass over volume. The mass wouldn't be able to identify them because they're both 5-gram samples, and even if they weren't both 5-gram samples, they have the same mass to volume ratio. Meaning if I have double the mass, I have double the volume. So the mass can't identify chemicals based upon their mass in any case. Okay, we can't identify something based on its volume alone. All right, we can have, if I said to you, I have 10 liters of a liquid, what's the compound? You can't identify anything based upon volume alone. Now you can identify things based upon their mass and the volume that that mass takes up to get the density, but in this case, we can't even do that. Okay, so party people, it's important to realize that we cannot identify by volume either. We can't identify anything by temperature, right? I mean, um, if one object is at 30 degrees Celsius, another object is at 32, that doesn't mean anything. Now, the change in temperature, how the temperature will change based on a known amount of energy, hey, that's specific heat, that's different. But this raw temperature, you can't identify, differentiate between two samples of two different compounds based on their temperatures alone. So the only thing left that makes sense is solubility, okay? And different ionic compounds will definitely have different abilities to dissolve in water. In fact, we have a table, table G, that shows that. So 10 is 4, but let's go to table G for a second so you recognize that they're really going after that kind of understanding. So table G here has salts, positive potassium ion, positive 1 with a -1 iodine atom. Hey, we got a negative nitrate ion from table E and K+. Okay, same thing here. These are all salts. Almost all of them are salts except for a couple of molecules. Nonmetal molecule. Okay, also SO2 molecule. Okay, so this is showing at different temperatures the solubility, which shows you how much we can dissolve. So if you notice, potassium chlorate, ClO3, we can potassium, and it's the chlorate that's given to us in table E. We can see that at 60 degrees Celsius, about how much? Oh, about 28 grams of potassium chlorate can be dissolved completely, maximally, saturated solution at 60 in 100 grams of water. But notice potassium nitrate, a curve much higher at the same temperature, okay, it can dissolve about 105 grams, can dissolve in 100 grams of water at the same temperature, which is more soluble. So how well the water can dissolve these ions is solubility, and that's another physical property of ionic compounds, and one that you could definitely have identified. Okay, those two salts with them. If two of those salts were one of these salts listed on this table, and you knew its solubility in 100 grams of water for a particular temperature, you could have identified them. Okay, that's called a physical intensive property. So 10 is definitely 4 there, even though I circled all of them with that little circle there. So 10 is definitely 4. Okay, so moving on to number 11. Number 11. What is the number of electrons shared between the atoms of an I2 molecule? So let's do a Lewis dot diagram. So iodine, and we should know it's in row 17. And if you do not know that, you go to table reference table. It's a halogen, and its last electron is 7, so it has 7 valence electrons. So we write that 1, 2, 3, 4, 5, 6, 7. It's a nonmetal, so it's going to be forced to share. There's not going to be a transfer of electrons, okay? And so another iodine with 7 valence electrons would be 1, 2, 3, 4, 5, 6, and 7. And notice by sharing, and you don't need circles to do this, but by sharing, this iodine feels like it has the 8 that fills its octet. All right. All right. So they both, by bringing one electron to the table, both feel like they have 8 in their outermost shell. Okay, what makes them feel like a noble gas counterpart in their row. Any case, that being stated, how many electrons shared? Well, one bond is a pair. Okay. Now, shared between is what they're looking for. So obviously, this one feels like it has 8. This one feels, but they're sharing right in the middle here 2 electrons. Now, careful with this question. Sometimes I've seen the same question, but sometimes they'll say how many pairs. Okay, so careful. When I see this question and I'm doing these tests, I say, ooh, they're looking at pairs or just how many electrons? In this case, it was total number of electrons. But if it was pairs, it could have been the answer could have been 1. So in any case, number 11 is 2. Okay, number 12. Which substance? Now, a substance is either going to be an element, okay, or a compound. Now, in this course, an element could be something diatomic, like in this case, Cl2. Compounds have two or more different atoms. Elements are bonded to the same atoms, okay? So this would be the element, and 2, 3, and 4, those choices are compounds. You should know what a substance is. Now, careful. Some people see nonpolar and say, oh, symmetrical. Okay, and so I see a lot of people will circle 4 and say that must be the answer. When you hear nonpolar or polar, you have to distinguish between, are they talking about the bond or are they talking about the molecule? If they're talking about the entire molecule, 4 would be the answer. But here they're talking about the bond. So what's going on here? What is a nonpolar covalent? Covalent sharing between two nonmetals that are forced to share because they have strong electronegativity, strong attraction for other people's electrons. Attraction, electronegativity, and other important words that are popping up here in this review. So if you look at chlorine, let's do chlorine. So Cl2 and another Cl2, and we know that chlorine has 7 valence electrons, and this chlorine has 7 valence electrons, and it's a nice little match made in heaven here. They both, by bringing 1 electron to each other, both feel like they're sharing 8. But because they both have the same electronegativity, now I could look it up on table S, okay, but it doesn't matter. They're the same element, so they're going to have the same attraction. So this pair of electrons here is equally pulled in this direction as it is pulled in this direction because these both have the same electronegativity. So therefore, these electrons are shared equally. And because they're shared equally, across this bond, no one side of the bond has more electrons than the other. So this is called a non-polar bond or non-polar covalent bond. The molecule, this is not a molecule in this case, in this course, it's an element. So this is the answer. Now if you look at choice 2, SO3. So if we took 3 O's, and just for all intents and purposes, for time's sake, we're not going to do the whole Lewis dot diagram, but oxygen is more electronegative than sulfur. Okay, oxygen is about 3.5 and sulfur is about 3.0. So the electrons bonded between sulfur and oxygens are pulled closer to the oxygens because they are more electronegative. So this side of the bond, okay, this side of the bond is going to be more negative or electron rich than this side. And that's what we call a polar bond. The differences between the elements, they're going to feel different charges. In this case, you don't because they're shared equally, and this is shared unequally. Again, we're not talking about molecule, we're talking about the bond. You have to be careful when you hear polar versus nonpolar. So for silicon dioxide, same idea. Okay, these are two different nonmetals. Guess what? They have two different electronegativities, so they're going to share unequally. Hello, carbon and chlorine, two different nonmetals, two different electronegativities, they're going to share unequally. The only one is the same, bonded to the same, with the same electronegativity that shares equally, therefore no one side has more electrons than the other, is the only nonpolar covalent bond. And you should sometimes you'll hear, hey, which of the following has unequal sharing? And that would be a polar covalent bond. And 2, 3, and 4 both have polar covalent bonds. Now, CCl4 is a non-polar molecule that has polar bonds because those polar bonds cancel by having the CLs in all directions. Another discussion for another day, but this was about the bonds. People get this wrong all the time. Number 13. Number 13, compared to a potassium atom, neutral. Okay, so K0 neutral. A potassium ion has what? Well, what charge is potassium ion? If you don't know and didn't know that potassium is a metal, the periodic table of elements is your friend. All right, so potassium, upper right-hand corner tells you the charge like to become. So potassium, like all metals, it becomes positive because it loses its valence electron to have that octet remaining. Okay, notice calcium, an alkaline earth metal, these guys all lose too. So something you should know, being in the same family, you have the same, what, oxidation states. Therefore, you bond similar. You have similar chemical reactivities. These alkali metals all are what? +1 because they all have 1 to lose, and they lose electrons because they hold on to electrons loosely. They have low attraction for electrons. These guys are the big atoms. So this guy loses electrons. So when a potassium atom becomes now positive, and it's important to know that, okay, that it goes positive. In order for it to go positive, like all metals, it loses an electron, it oxidizes. Losing electrons is oxidation. Now, when it loses an electron, okay, it's going to get smaller, okay? Now, why would it get smaller? It gets smaller because losing electrons means the remaining electrons feel the nucleus more and they get pulled in. Another easy way to remember something, if you lose weight, do you get bigger or smaller? You get smaller. So think of losing electrons, you get smaller. Okay, and if you gain weight, okay, you get bigger. So if I had a chlorine atom who's a nonmetals, these guys gain electrons to become chlorine negative. Okay, the chlorine negative ion is bigger than the atom or the atomic radius, because by gaining electrons, I'm gaining weight. One reason to remember that. But a nice part 2 way of explaining why K0 gets smaller when a K plus, and I've seen this a million times, these questions in multiple choice can become the part 2. So understand this, to become K plus, okay, from K0 and losing electrons, okay, you have what? A lower number of electrons in shells. Wasn't this 2-8-8-1? So you had 4 shells of electrons. Well, party person, K plus is now 2-8-8. So you have less shells of electrons. Therefore, you're going to be closer to the nucleus and thus smaller. If they say to you, why does K0 get smaller? You can just say, hey, it loses an electron. It's that simple. Okay? The best way to say, hey, it got smaller, it lost an electron, that's a Regents chemistry explanation. Why does chlorine get bigger when it gains electron? Because it gains an electron. Gaining electrons makes you bigger. Okay? Any case. All right? So, potassium ion, you had to know it was positive, so the reference table would tell you, or you can remember it was a metal, and all metals are positive because all metals like to oxidize, lose negatives to become positives. So a potassium ion does not have more or less protons. Bad choice there if you did that, because it's still potassium. What identifies potassium? Its proton number. So this is still 19. This is still 19. Okay, so potassium ion has a smaller radius, 13, okay, is definitely going to be choice 1. All right, so on to number 14. Number 14, somewhere, somehow on your test, they're going to somehow see if you know what average kinetic energy is. Now, average is important because molecules of gases don't all move at the same velocity or speed. But if you take in all their motion energy collectively and average it, we call kinetic energy the motion energy. So average kinetic motion energy is essentially, in this course, equal to temperature. That's an important one. Just like this would be URE, okay? Just like attractions for electrons is electronegativity. If you don't know, table S does that. So average kinetic energy, temperature. And so kinetic energy is motion, okay? It's the physical motion. So which is the form of energy associated with the random motion, the kinetic energy? So which choice is closest to temperature? Thermal. Okay, thermal means how hot or how cold or how much temperature something has. A thermal change is a temperature change. Okay, a thermos keeps the heat in. So 4 is that answer there. All right, so 14 is 4. On to number 15. Number 15, the average kinetic energy, hello, that equals temperature. Get that down. You're going to see it. Decreases. So basically, they just want to know which one is a temperature decrease. All right, now careful, sometimes they have Celsius plus kelvins here. In this case, they kept life nice and simple by keeping the kelvins or having the temperature in the same unit. In table T, we could have converted kelvins to Celsius. We don't have to. Kelvins is that positive absolute scale that starts from a true zero position, meaning at 0 Kelvin, there is no more what? No more motion. Okay, there's no more movement, no more kinetic energy. But we want to decrease the temperature. So we're going to go from high temperature to low temperature. So choice 1, look at choice 2. We're staying the same. Temperature staying the same. Look at this one. 200 is going to 273. That's going up. That's an increase. 273 staying the same. So the only choice where the average kinetic energy of water molecule is decreasing is choice 1. The temperature is decreasing. I don't care about what the phase changes are or not here. Totally inconsequential. If I was asking for potential energy, okay, then that'll be a different story. I wouldn't even look at the temperature. I would look at the phase changes. And I know that gases, or as I like to say, gas, has higher, this is a gas, a liquid, and a solid. So a liquid going to solid is a great change of potential energy because gases have more potential to move than liquids. But this was all about, can you identify that average kinetic energy is temperature? Get it down, write it down. And that they just wanted it decreasing, that simple. 15 is 1. On to number 16. Number 16, the joule is a unit of, well, if you don't remember your kinetics and equilibrium chapter, okay, it is energy. Now, you say, okay, I should have known that. But you know what? There is a table on the reference table that goes off the most used units in this course. Let's go there. So table D is your friend in this question. Okay, even if you never knew it was there, now you do. So symbol, name, joule, and it's a quantity of energy right there. Who's to say that these other questions, or there's other questions I've seen, a couple of them, that could pop up here for these selective units that we use throughout the course, okay? So any case, I'll say another one that comes up all the time, or at least it seems like in the last few tests, they've been using this weird U for atomic mass unit, like carbon 12, okay, has 12 U's. Now why? Because, well, this is a protons. These are protons and neutrons because protons and neutrons have the same mass, so they have 12 units of mass, okay? And all the mass of the atom is due to the protons and the neutrons combined. All right, so that's where you could have used, that's where you could have looked for a unit if you weren't sure, and you probably have never used that table before, and now you know. So 16 is 2. Compared to a sample of helium at STP, so now we're at number 17, sorry. So number 17, compared to a sample of helium at STP, that's standard temperature, which is 0 degrees Celsius or 273 Kelvin, standard pressure, 1 atmosphere, or 101.3 kilopascals, which is given to you in table A. All right, the same sample of helium at a higher temperature and a lower pressure does what? So now we have a sample of helium at 0 degrees Celsius, 1 atmosphere. The same sample of helium is now going to be heated, okay? And it's going to have a lower pressure on it. So somehow we're going to make these helium atoms, who are noble gas, doesn't react. They're monoatomic molecules sometimes people call them. Any case, we're going to make them go faster. We're going to put less pressure on them, so this distance between them is going to increase. Okay, and so if we basically increase the distance of gases, either by increasing their temperature or decreasing the force due to other colliding molecules. Now, what do you mean by that? Well, if I have other colliding molecules hitting them, they're going to be forced to be closer together. If I decrease the pressure on this gas, okay, there's going to be a greater space between them. And therefore, we're going to have less of those other colliding gas molecules, or we could make the container wall bigger. We're going to allow for more distance in between them. So if these molecules can physically move farther apart because they're going faster, and they have the space to do so without having collisions either by the container walls or other molecules, then they are going to have less attractions. And if they have less attractions for each other, they're going to behave more like an ideal gas. Okay, so the big thing here, ideal gases are like ideal students. Okay, and that's the biggest thing you have to remember when you think about an ideal gas. I think of the ideal student, and there are basically four things that we think about, and let's make some room here. Okay, first of all, to be the ideal student, okay, you're going to move in straight line motion. Why are you going to move in straight line motion? Because you want to get to class as fast as possible. So you're going to move fast. You're going to go in a straight line motion. And by the way, you're not going to bend toward the other kids in your class. Like for instance, if I asked the ideal student to go grab the worksheets that are on another desk and pass them out to the class, they're going to go in a straight line. They're not going to spend any time talking to other students. A real student would take his time to do this and would probably take a detour before they got to the worksheets, and talk to their friends, and they would go in curve lines. All right, so the ideal student would get to the worksheets and back, whereas the real student would say, hey, what's up, party people, what's up, girlfriend, and then get to them and move in it because they're attracted. Okay, and that's the biggest thing, is that a real gas really has attractions, and ideal gas has no attractions between them. That's the fourth postulate. Now, as these students leave class, they want to get to the next class really fast. So they go really fast, they go in straight line motions. Oftentimes they collide. So their collisions are important to talk about. Their collisions, we say, are elastic, which means they bump into people and they bump off them and keep going without saying anything because they want to get there so fast. And because of these elastic collisions of molecules slamming into another, and then bouncing them off, energy is conserved. A real gas would bump into somebody, but then they would stick together because that real student that would say, hey, how's it going? Yeah, okay. And because there is what in real students and real, there is attractions. And so real gases would have inelastic collisions, kind of like a bullet hitting a board, okay, and all the energy is absorbed by the board, okay. So here there's going to be basically like a pool, if you ever played pool, where the eight ball hits the cue ball hits the eight ball and it ricochets off, okay. And then three, we say the molecules have no significant volume. And why do we say that? Well, we say that because these particles are so small, the space between these particles is so great that their own space where they're flying in is insignificant. Okay, so the granddaddy of all postulates that support the ideal student, the ideal gas behavior, is that gases that are ideal, okay, have no attraction. And that's the reason why all of this works. Kinetic molecular theory is what this is basically talking about. Kinetic molecular theory basically shows how the gases, or describes why they behave like they do. And why do we care about ideal and real gases? Because our gas laws, which in this course you only have PV over T equals PV over T, our gas laws work mathematically perfect only when our gases are behaving like a perfect ideal gas, which means if they have, and which we know this to be true because, well, guess what? There is no such thing as an ideal gas. We can always increase their behavior. So our gas laws don't work perfectly. There is some deviation. Our mathematics that we do in your gas laws don't work out perfectly because there is some volume. There is some attractive forces. So how much we're off depends upon how real the gases are. And how much we're closer to these calculations depends upon how ideal they are. So that's why choice 4 is the best answer. Okay. And if you look at your other choices, condenses to a liquid, how would gases condense to a liquid? Well, they have to attract each other. And attractions, of course, are what real gases do. More soluble in water, that means that the gas is attracting water. Okay, forms diatomic molecules, it's bonding to each other. That's not what we're talking about here. Okay, so 17 is 4. On to 18. Number 18. A sample of gas is in a sealed, rigid container. Hey, it's in a container that just won't move, okay? That maintains a constant volume. Which changes occur when gas particles is heated? Okay, well, heated, it means we're going to increase the temperature. We know temperature is equal to the average kinetic energy. Keep saying it because people still get it wrong. Average kinetic. Now, kinetic is motion energy. So we're going to increase the motion of these particles, going to make them go faster. So if you make particles go faster in this same size container, then they're going to collide with each other more often. So the frequency of collisions has to increase. That's why we get rid of 3 and 4. That's why we should know something. Hey, as temperature goes up, the pressure goes up. And it's a proportionate relationship if what? Temperature is Kelvin, okay? So yeah, make them go faster. What's pressure? Pressure is due to the number of force being provided over an area. And the force is provided by the collisions. And so if you move faster, they collide more often. Now the next part of this is, what happens to the force of collisions? Well, the force of each collision is going to increase. If I have a car or a ball hitting a wall, okay, and I make them go faster, wouldn't that individual collision have more force if the molecule has more speed? Absolutely. Okay, it's purely intuitive here. So 2 is the best answer. Make the molecules go faster, they collide more often, which increases the pressure, and each individual collision with the container wall increases because each particle has more speed. So 18 is 2. Moving on to 19. Number 19, I call this the same problem. Comes up a lot. At STP, standard temperature and pressure, outlined in Table A, which gaseous sample has the same number of molecules as 3 liters of N2? This is Avogadro's hypothesis. If you have the same volume, okay, for any different gas, but those gases, those 2 different gases, are at the same conditions of temperature and pressure, we're saying both of these are at the same STP values, then what do we know? The number of molecules is the same. What is 1 mole of any gas that can, what's the volume that 1 mole of any gas can occupy? And you should know that 1 mole of gas at STP occupies 22.4 liters. So if I have 1 mole of helium and I have 1 mole of hydrogen, I don't care if it's H bonded with H or helium hanging out, these both, if they're both at STP, will occupy the same volume. Same volume, same number of molecules. Well, what's a mole? Mole is actually 6.02 times 10 to the 23 number of particles, not atoms, particle. In this case, that's an atom, it's a particle. This is a particle of 2 atoms. Okay, and we call those molecules. So, same volume, same number of moles, same number. So if I have 3 liters and I want the same number of molecules, I would need 3 liters of another gas. Same volume, same temperature and pressure, same number of particles. In the case of helium, it's just an individual atom as a particle. In the case of hydrogen, it's 2 H's that are a particle. Do not fall in love with the idea that you're going to same number of atoms, same number of molecules. Avogadro's hypothesis. Same volume, same temperature and pressure for the gases, same number of molecules. Same molecules, same volumes if the gases are at the same temperature and pressure. So 19 is 3. And basically, it's how we came up with the mole using Amedeo Avogadro's hypothesis. Okay, so 19 is 3. On to 20. Number 20, distillation of crude oil. They love talking about this. First of all, distillation is a separation technique. And we have several that you're responsible for knowing. Separation of what? Separation of a mixture, right? A mixture is two or more substances that are not chemically combined. They're just put together, guess what? In a mixture. Sand and water. Okay, crude oil is an example. What's in crude oil? You have gasoline, you have kerosene, you've got diesel fuel, you have all different types. You have waxes, you have the tar, you have the asphalt. All of that's part of plastics. All of those things come from crude oil. And crude oil is basically a mixture of all these different type of substances. Now the substances in crude oil are all different compounds. We have different chemical formulas of things that are mixed together from crude oil. Distillation separates things that can be boiled off very easily. So distillation separates things that have different boiling points, different vapor pressures. The most famous type of distillation, if you watch the show, um, one of the shows, I guess, in I forget who broadcast them, but the Moonshiner show, where people are making moonshine in the woods, and basically what they do is they take sugar and what they call they put yeast and they produce the alcohol. And it's part of the reactions you should be knowing. We make ethanol, right? We make ethanol, and ethanol does vaporize pretty easily, and it's in water. And to purify the ethanol to make the moonshine, they boil off and separate the ethanol from all the stuff they mix together, the yeast and the corn maybe, to separate the ethanol. Now, water does go with it a little bit, but to try to separate the alcohol, the moonshine, from the mash, I guess they call it in that show, they distill it. Okay, in fact, in class, we separated water from Coke by running distillation. Okay, so it's a way to separate a mixture of liquids based upon different boiling points. Remember, it's very important to understand that in a mixture, the individual components of a mixture retain their individual properties. So therefore, water will still boil, okay, at its relative boiling point, and whereas the other compounds will keep their own properties. So you can boil off the different components if they're not chemically combined, because if they're chemically combined, no longer is this a mixture, and this would need a chemical change. So we have distillation of crude oil from various parts of the world yields different percentages of hydrocarbons. All they're saying is that when we separate the components of the compounds of the mixture, the gasoline, the kerosene, we're getting different amounts of, let's say, the gas, or the different percentages of gasoline, different percentages of kerosene, different percentages of wax. Okay, so how do we explain these? Okay, well, look at the choices. Each component of a mixture has different solubilities of water. See, that's true, and it's a good distractor, because each component of a mixture is a different what? Is a different type of substance, which is going to have its own unique properties, and it retains their own properties. So this is a very good distractor, but it's not correct, because why would separating a mixture of different compounds, okay, yield different amounts of those compounds? Well, doesn't mean that they have different they do have different solubility, but doesn't explain why you have different amounts. Hydrocarbons are organic compounds. That's true, but it doesn't answer the question. The carbons in hydrocarbons may be bonded in chains or rings. That's true, but doesn't answer the question. So 4 must be correct by process of elimination, but it should make sense here. The proportions of components of a mixture can vary, right? If I make a mixture, okay, and if I dig crude oil in different places in the world, there's going to be a different percentage of gasoline in that mixture, of diesel fuel, of waxes. And that's a very important part or a component of a mixtures. Mixtures are made physically, they're separated physically, and distillation is one type of physical separation because they're not chemically bonded between the compounds. They're just mixed. And their proportions can vary. Think about this. We can have a very dilute mixture of sugar water, or we can have a very concentrated. They all make homogeneous mixtures by dissolving in water, but you can change their concentrations. And hence, that's why we have this thing called molarity, which is moles of the substance being dissolved over a liter of solution. You can, as long as you are not getting past the saturation point, we can have any molarity of any what? Solution, okay? Because again, it's a mixture and it can vary. What cannot vary is a compound. For instance, C6H12O6. This is a chemical compound of glucose. You can't have C5H12. It must be this arrangement. Okay, so compounds cannot vary in how they bond with each other. Mixtures can vary in how they're mixed, obviously. All right, so that's what that question was really after. Did you know the identify distillation as a separatory technique, and did you know some basics of how a mixture and a compounds differ? Now, what are the other separatory techniques besides distillation? Well, we have chromatography. We can separate chromatography based upon solubility, right? Remember we had a mobile phase? And we can have the components of a mixture either choose the non-polar mobile phase or stay with the polar backing of the silicate plate. Okay, we can also just do evaporation, boil off the water from a saltwater solution. Those are examples. Or we can do a physical filtration, and we can physically separate precipitate from a solution as another way to separate mixtures. Okay, that's what this question was about. Number 21. Number 21. In which 1 gram sample are the particles arranged in a crystal structure? Hello, crystal. That means solid. All solids have a regular repeating geometric structure. Okay? And therefore, that's why 1 is the answer. Gases do not have a crystalline structure. Liquids do not. And this is just a homogeneous mixture of calcium iodide dissolved in water. If you boiled off the water, which would be a separatory technique, separation of this mixture, okay, you could get one. So regular repeating arrangement of molecules, atoms, or ions is what a solid does. Get that down, because they could ask you to draw, okay, an example of a particle arrangement of a solid, and you'd have some kind of repeating arrangement. Liquids do not have a unique structure, even though they may have strong attractive forces. Okay, so 21 is, could you identify that solids are all made of crystal or some kind of repeating geometric structure that repeats over and over again? A crystal lattice is what we call it mostly. So number 21 is 1. Number 22. Number 22, when a reversible reaction is at equilibrium, the concentrations of products and the concentrations of reactions must be, most students will pick equal because they see equilibrium, and that is so wrong. What is equilibrium? Equilibrium is the rate of the forward reaction equal the rate of the reverse. And it doesn't have to be a chemical reaction. It could be a phase change. I could have CO2 aqueous, that's dissolved CO2, let's say in soda, becomes CO2, as I like to say, gas. Now, if the bottle is closed, as fast as some of this aqueous escapes into the gas phase, some of this gas phase goes back. I also like to say, hey, what if I've got 10 people on this line? And I have 2 people on this line. And I ask one person from each line to change places every minute. After 100 minutes, okay, won't I still have 10 people on this line? Won't I still have 2 people on this line? And the answer is yes. If we're at equilibrium, the rate of this line going to this line is as fast as the rate of this line going to this line. So the number of people on each line stay constant. That's what this is about. So it's not about equal amounts of products and reactants. It's almost never going to be equal, these lines in equilibrium. Okay? It's about that the amount of these stay constant. And they do so because what is really equal here? What's equal is the rate of the forward reaction equals the rate of the reverse. We talked about catchphrases in this course. Average kinetic energy is temperature. Attraction for electrons is electronegativity. Well, when you hear about equilibrium, the rate of the forward equals the rate of the reverse, and because of that, the amount of reactants and products stay in a constant state. It doesn't mean they're not changing what? Lines, but the amount of them stay constant because the rate of the forward equals the rate of the reverse. That's another very important. This could be a part 2 question where they ask you explain why, and you would say, hey, the rate of the forward equals the rate of the reverse. Okay, therefore the amount of each has to stay constant. 22 is 3. Moving on to 23. Number 23. In chemical reactions, the difference between the potential energy of the products and the potential energy of the reactants is equal to. Another classic kind of a definition question, but if you remember your potential energy curves, okay? So this is potential energy. We track an exo or endothermic reaction. This is some kind of time coordinate, okay? If we have an exothermic reaction, we're starting with some what? Reactants that are unstable, high energy, something that can explode, has high potential. And after the reaction's over, we wound up with products that have lower energy, they're more stable. And the reactant pathway looks something like this. And so what is delta H? Delta H is the difference of where you start and where you finish. So this difference here is the heat of reaction. And that's that difference they're looking for. Delta H is the difference of where you start and where you finish. So if you knew your potential energy diagrams, you would know that the difference between the potential energy of the products, by the way, this is the potential energy of the products, this line right here, and the potential energy of the reactants. That's this line right here. If you subtract these two lines, that's what you have here, and that's delta H. It's a change of H, and by the way, it's going down, and that's why for exothermic reactions, okay, it's negative. Okay, so this would be the heat of reaction. It's a straight definition, but you can apply that definition to other things that you know. So heat of reaction, delta H, also called enthalpy, but you probably won't see it that often. And it's difference of where you start to where you finish. And if you subtract, like for instance, if this is 100 right here to this line, and this was 20 right here, delta H should be negative 80 because we do products minus reactants, and this would be negative 80. And the reason why we do products minus reactants, we want that negative sign to reflect going down. That's why it's products minus reactants, okay? So again, you can memorize it or you can just understand it and be able to use it anytime you want. That's what I'm after here with going over with this with you. So 23, okay, is 3. On to 24. So number 24. What occurs when a catalyst is added to a chemical reaction? So a catalyst, we should know, is going to speed up a reaction. And what it does is, in looking at a potential energy curve that we used for 23, a catalyst is going to lower the activation energy. Activation energy, it's going to change this pathway. For instance, in this reaction without the catalyst, the activation energy you need to start the reaction would be from the top of the hill to where you start. So it would be this value right here. Now, if I add a catalyst like I did in blue, it's going to change the pathway. It's not going to change the difference where we start and finish. The delta H does not change. It just changes the size of this pathway or this hump, and it lowers that activation energy from where you start to the top of the hill. Well, now the activation energy has been lowered because now this reaction pathway has an alternative pathway that overall requires less energy to start the reaction. And so there is always a amount of energy available to chemical reactions, whether it's you're adding heat by a hot plate or just using the ambient temperature of the room. So if each collision, remember these reactions occur because of collisions, occur and require some amount of activation energy, from the amount of energy that's available, you'll get more what? Collisions and more reactions faster. So we say that an alternative reaction pathway definitely occurs. Can't be the same. The pathway is here. Why do I say pathway? Where you start and where you finish is called a state function. The pathway is how you get from one to the other. Remember, delta H is, I don't care what pathway you take, where you start, where you finish, that's delta H. So the catalyst changes the pathway, which is that energy barrier for the reaction to occur. So that's why 3 and 4 we get rid of. Now, and you're going to lower the activation energy because you're going to lower this little line here that you have to identify. Remember, activation energy is the energy it takes to go from where you start to the top of that crest, which is, by the way, called the activated complex. So we lowered the activation energy with a catalyst by changing its pathway. Classic statement right here. And 24, as I've been saying this for other choices, if they were to give this in part 2, they'd be expecting to say one of the two things. Hey, the catalyst, why does the catalyst speed up a reaction? You would say that it lowers activation energy. That'd be great. You could say it finds an alternative reaction pathway. That'd be great too. Okay, so these types of answers or these types of questions in multiple choice are the same answers in the free response section. Okay, so on to number 25. Number 25, what is the name of the compound with this formula? Okay, well, I see hydrocarbons and I see an N. So ding, 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 this is an organic question. And I know that I have a bunch of reference tables. In fact, this is a function on a hydrocarbon. When I say function or functional group, there's a certain type of bonding of a certain type of arrangement of atoms and types of atoms that go on a hydrocarbon chain that make this a functional group. So I've got to go to my functional group reference table, which is table R. Now, just so I can weed out some things, we should know from table P that 1, 2, 3 carbons is prop, and they all have prop. Okay, the question is, what would this be? So let's go to table R and see if we can match the type. Now, if I'm looking at this for a second, this right here could be an R, the rest of an organic molecule. And then I've got an N here, okay? And then I probably could have other R's for the rest of an organic molecule. So I'm looking for that kind of general function, rest of the organic molecule. Let's go to the table R. So I'm looking at table R, all right? And you notice the rest of an organic molecule, like we just talked about, and looks like this is an amine. In fact, this is exactly, okay, what we had in the question. All right. So this is a question. Do you know that there was a table of functional groups that you could have matched this up? And so this is an N bonded with a bunch of C's. It's one prop because it's 1, 2, 3. And how do I know prop is 3? Table what? Table P tells you that. So that's a prop. We put a 1 in front because this N is attached to the first carbon. And why is it not the 3? The IUPAC naming system, when you name things attaching to a hydrocarbon chain, which is basically all of the naming, we put the attaching group on the lowest number possible. So this is propane, propaneamide. These are single bonds, and that's just what it is right there. Just match it with table R. So 25 is 2, 1 propanamine, just as it was just given to you from table R. Okay, and number 26. Number 26. Which compound is an isomer of this? Iso means same, just like isotope, same atom, different number of neutrons. Isomer means same chemical formula or molecular formula. This is the formula of exactly how the molecule, number of atoms, but actually this is a structural formula, okay? So showing the structure of how they bond, which other structure has a different structure but same number of atoms. So what I have here is 2 carbons, so C4. I'm just going to write a molecular formula. I have H10 and 1 O. So this is my molecular formula. So I need something with 4 carbons. Well, look at choice 1, 1, 2. Can't do that. Okay, this one has 2, 1, 2, 3, 4. That's a possibility, but it has 2 oxygens. Only have 1 oxygen. Okay, and let's check out here. Number 3, I need 4 carbons. This one has 3 plus 1 plus 1, 5 carbons. So it can only be 4. Let's just check anyway. 4 carbons, 10 H's. There's a 9 plus 1 and O, so 4 is our answer. Again, isomer. Same number of atoms, different structure. This, of course, is an ether structure from table R, and this is an alcohol structure. All have the same molecular formula. Important for you guys to recognize that this structure, although with the same molecular formula as number 4, will have different chemical and different physical properties. And they could ask you why in part 2, and you would say different structures, different chemical and physical properties, because structure is king in organic chemistry. Change the structure, you change the properties. That's king. King, I can do this. Okay. All right. Number 27. Number 27, ethanoic acid and 1-butanol can react to produce water and a compound classified as what? All right, well, this is an example of esterification if you don't remember. Now, ethanoic acid, what is that? Well, that's 2 carbons, and it's the acid. Boy, if you go to table R, you'll see that ethanoic acid is 2 carbons, and it's got this Cu group or carboxylic ending. And all I'm using is table R to help me with that. Notice carbon makes 4 bonds. Okay, and these dashes would have H's. Bute from table P, okay, has 4 carbons. And I put single bonds because of the ane. The OL ending in table R is an alcohol, and it's 1 butanol, so the ending alcohol has an OH group. Fill in the rest with all the carbons with 4 other bonds, which are what? Hydrogens. And so we should remember that the water is going to come out, and we're going to push these guys together. So the water leaves, as they said, it's a dehydration synthesis. And what we're going to have is we're going to have the carbon right here with this C double bond to the O, bonds to this O, and then what? 4 more C's. And what we made, party people, if you can't see, is an ester. And what's an ester? Okay, well, you have an R. This is one R here, bonded to a C, double bonded to an O, to another R. It's or R prime to show a different R group. Okay, this is one R group. This is the rest of the other. Okay, that's what we have here. And this is a middle compound. And if you do not know what this was, you go to table R and you would see that this is an ester. Esterification, okay, is the process where we take an organic acid with an alcohol, take out the water, and make a bigger particle. And this molecule that we're making has 2 O's in the middle, one carbonyl carbon double bond to an O with an O. Okay, and some people recognize that right away and move on because they know that's a reaction that they see often. All right, so that's just something you have to know. Now you should be able to actually, they could have asked you in part 2 to name this. Okay, so let's go over the naming portion of this. When you name an ester, now table R shows an example, but to name the ester, you must name the alcohol portion first. So this is bute. So this would be bute, and you add the YL, butyl, and the acid part gets an OAT ending. So this would be ethanoate. And how do I know it's an OAT ending? Okay, table R gives you that example, not exact example. And something else you should know about ester. So butyl ethanoate. The alcohol is named first, the acid part. Something else you should know, this is an aromatic compound that can come up. These are the sweet smells of nature. The smells of flowers are esters. Okay, and that's really all you've got to know there. Okay, so number 27 is 3. Number 28. Number 28. During an oxidation reduction reaction, number of electrons gained is equal to the number of electrons lost. Why? Because there's conservation of mass in reactions. There's conservation of energy always as well for chemical reactions. And there's conservation of charge. We've seen this in the problem. When you do half reactions, okay, for instance, if I had copper plus 1, gaining an electron is reduction, becomes copper 0. And I had zinc oxidizing, which becomes zinc, okay, plus 2 electrons. Notice the electrons given off and absorbed are not the same. So what we do is we multiply this one by 2 to give it 2 electrons. And the electrons cancel. And we're left with an overall reaction of 2 copper plus 1 plus zinc 0 gives us zinc plus 2 copper zeros. And charge is plus 2 on this side, and it's plus 2 on this side. And why? Because the electrons that are absorbed, okay, are the same that are accepted. Have to be. That's how it works. If that's not the case, then we're destroying and creating electrons in every redox reaction, and that's not the case. We don't destroy and create matter, we don't destroy and create energy, and we don't destroy and create electrons. So 28 is 1. In your half reactions, they must always be equal. Number 29. Number 29. Which process requires energy for a non-spontaneous redox reaction to occur? Well, first and foremost, redox reactions are chemical reactions. Chemical reactions mean you're making a brand new substance by essentially messing with electrons. This is not a nuclear reaction, so we get rid of alpha decay. Alpha decay is when you have some type of alpha particle being emitted. I'm down here now in the bottom of the page. And an alpha particle is going to change the nucleus. Nuclear reactions are not chemical. They're not dealing with electrons. They're dealing with the actual nucleus becoming more stable. So get this in your heads that any kind of nuclear decay, beta decay, alpha decay, fission, fusion is not a chemical reaction. Redox reactions are chemical reactions. Now, chromatography is a separatory technique. We've talked about distillation earlier. If I want to separate a liquid, let's say ink, and I plate a TLC plate with ink, black ink, which is made up of actually many different colors of ink, right? And what's going to happen is we put that in a container and we have some kind of nonpolar solvent that gets pulled up the container, pulled up through the plate. This plate has a silica backing, which is mostly polar. So we're going to give the mixture of an ink a choice to go with the nonpolar solvent or stay with the polar plate. And based upon solubility differences, we'll separate the inks on how far they go up. But it's a separatory technique. This is physical because this is a mixture. Chromatography uses mixture. And we separate mixtures physically. We separate what? Compounds chemically. So this is a physical change and not a chemical reaction. So chromatography is out the window. Deposition is a word that people forget all the time. So let's review it. When we have H2O, is a good example, H2O liquid, okay, I'm sorry, gas, go directly into H2O solid. It's the opposite of sublimation. So when gas goes to solid in that type of, guess what, physical change, because we're not changing the chemical formula, we call it deposition. When a solid goes directly to a gas, that's called sublimation. Everyone forgets deposition. So that's a bad choice because that's a physical change. So if you look at your terrible distractors, okay, and I'm sorry if you got one of them, you picked one of them, okay, they are not talking about any kind of chemical reaction. Redox reaction is a type of chemical reaction, although it's the most prevalent. Most reactions are redox reactions. So in any case, and by the way, deposition, the greatest example of a gas going to a solid is snowing. Water vapor in a cloud going directly into a solid is what snowing is. So get that in your head because you will see deposition popping up. And sublimation, greatest example would be CO2 solid, okay, going to CO2 gas, and they call this dry ice because it skips the liquid phase. So the answer, of course, by process elimination is electrolysis. And if you remember, electrolysis, okay, is that electrochemical cell where we a battery to force the reaction to go. So here's my voltaic cell, my battery. It's got two electrodes. Okay, and let's just draw an example. There's a couple different ways we can do this, but I'm going to electroplate something. And I'm going to electroplate my chicken fork, my famous chicken fork. All right, and I want to make it gold plated. So I've got a bar of gold. Who doesn't? Okay, now I'm going to connect these metals by a conductor. Okay, and we are going to make this the anode of the battery. The battery is spontaneous, and this anode is negative because electrons come out of it. And we know electrons flow from the anode to the cathode. So this must be the cathode of the electrolytic cell. Do not forget that anox, red cat. So at their cathode we have reduction. And just to kind of review this quickly, why not? This is the cathode of the battery, which is positively charged because electrons kind of flow toward it, right? So we're going to have electrons flow from the anode of the electrolytic cell to the cathode. And by the way, the anode is negative and it forces the electrolytic cell, this one, to be negative. And this positive cathode of the battery forces the anode to be positive, right? Because if we cut these wires, these wouldn't have any charge. And we're pumping electrons from the anode, so electrons are here. And we're doing that spontaneously. We're using the energy. Remember, electrolytic cells require the energy. They're like endothermic. Now, this wouldn't work. Now, what's being happening is the cathode is actually pulling and forcing gold to oxidize. So gold, 0, is being forced to give up 3 electrons, let's just say, and become Au plus 3. So a piece of the solid metal sends its electrons to the cathode, becomes aqueous Au plus 3, and then that's the part that we need energy for, to force gold to oxidize. That's what the battery is really there for. Once it oxidizes, this plus 3 is going to move to these 3 electrons and plate and make this electrode bigger. So the battery forces something that normally doesn't occur naturally because it requires energy. Gold does not like to oxidize, so we're forcing its hand by adding the energy. And that's why the answer is electrolysis. So that's why 29 is 2. Number 30. Which pair of compounds represents one arrhenius acid and one arrhenius base? Okay. Oh my God. Who is this person? Very simple. Arrhenius, A. The first letter of the alphabet is the first what? The first definition. First definition of acids and bases. All right. And since it's Arrhenius A, it's the first definition, which means it's the easiest. It's the most simplest. Okay? So therefore, to be an acid, you should know that you're giving off H pluses. Okay? And to denote what's an H plus giver is something with an H in front. Okay? And this chemical has an H in front, and this has an H in front. And so those are all my acids. Those are my Arrhenius acids because all of them will produce an H plus in solution. But if I didn't know that, I can go to table K. So let's go there. So table K lists your common acids. Okay, notice they all have what? H's in front. That just shows it that they give off H pluses. These are all Arrhenius acids. Okay, now notice something. As written, CO2 is an acid because it's in the table, but it's not an Arrhenius acid because it has no H's to give. So it doesn't fit that definition. Arrhenius was the most simplest. It wasn't the best definition that included all of them. Okay. Now table L lists common bases, and to be a base, you have to be a salt, an ionic compound that dissociates a hydroxide ion. The easiest definition of a base is somehow you produce OH minuses. These are all OH minuses. If you notice, NH3 is listed as a base, but it doesn't have a hydroxide ion, so it's not an Arrhenius base. So back to the question, we need an Arrhenius acid, Arrhenius base. Well, we found our acids with the H in front, and table K was our guide, and our L. And then we went to K to find our bases, and we have our salts with our bases. That's a base. That's a base. These are not bases, okay? These are alcohols, and they love to confuse you and love to put alcohols with these types of questions. Now, what's an alcohol? It's got a rest of an organic compound, so some kind of hydrocarbon with an OH. It's covalently bonded. It's not ionically bonded. To be a base or Arrhenius base, you have to produce hydroxide ions. So this salt, NaOH, breaks apart in OH minus and Na plus, right? This acid breaks apart into H plus and NO3 minus. These are ions, and they're also called electrolytes, acids and bases, because they break. This is not a base. It is not an electrolyte. It does not dissociate into hydroxide ions because it's covalently bonded. They love to throw alcohol. So how do I identify an alcohol? Some kind of hydrocarbon, carbons and hydrogen, okay? And then all of a sudden you see an OH. That is an alcohol. This is a base, calcium hydroxide. You see a metal with the hydroxide ion from table E. That's Arrhenius base. But great examples are from the tables I just showed you. So in any case, they wanted an acid, okay, which was, by the way, listed in our table K, and a base listed in table L and K, I'm sorry, right there. So choice 3 is the answer. We're going to move on to number 31. So we're starting in the part B1 section of the multiple choice, and this represents 20 questions that reviews the entire curriculum again, as 1 through 30 did, but supposedly these questions are a bit tougher, require a couple of steps, but let's go see, let's be crazy and start with 31. So 31, which electron configuration represents electrons of an atom of neon in the excited state? So the excited state represents electron configuration where electrons that were in their ground state, their lowest energy position, have been given energy and were able to pull away from the nucleus and exist in a energy state that's much higher. So you're going to look at an excited state configuration to identify that. You're looking for a configuration that's going out of order. And when I say out of order, I mean that in order to fill the second energy level, we know that the first energy level holds 2. So that to fill before we start putting electrons in the second shell, remember that after the dash here in the second shell, we have to have 2 here. So if you look at all your choices, we all have 2 there. For instance, 2-7 could be written 1-8. This would be ground state, and this would be excited state. That means an electron from the first energy shell jumped to the second. So that's what we're looking for. And if you notice, 2-7 goes in order in the sense that the first or the earlier energy shells are filled before we fill the second. Now in this case, what I just drew here was an example of what could be an excited state configuration right here. So I look at 1 and 2, these are ground state, they're going in order. Now I look at 3 and 4, I'm looking now, in order to fill the third, that's the third number, right? This is the first, second, and third shell, okay? I have to fill the what? The second. So if you look at number 3, which has to be the answer, okay, is that I have an electron in the third energy shell, yet the second energy shell, okay, still only has 7. We should know that the first energy shell holds a maximum of 2. The second holds 8. So in order for us to put an electron in the third, we should have filled this first. So 4 is showing a ground state configuration as we have filled the 8, and now we put an electron here. But 3 is excited state, which meant that electron from the second energy level must have jumped to the third. And that's what an excited state is. That meaning with energy, okay, we made an electron have a higher energy position. And as I said in earlier questions, electrons that exist farther from the nucleus, okay, need a higher energy to overcome this positive pulling force. And to identify an excited state configuration, you identify what I like to call as a hole, a place where electrons should be. This should be 2-8-1. But because this is a hole where a place should be, that means an electron jumped out of it to go farther away. We have no other positions like that with our configurations. However, I do want to take the time because you could see this question again and get confused. In this question, there's only one configuration that's going out of order, representing a hole where electrons should be, meaning electron jumped farther away when it gained energy to become a higher energy electron excited. But what if there were 2 there? Okay, because they said neon, we have to understand how many electrons an atom. When I say atom, you say neutral. We've been through this, hopefully. Okay, so this is a neutral atom, which means the electrons equal the protons to get an atom. So we're looking for something with the right number of electrons for neon. Let's go look at that. Neon being a noble gas in group 18, and there's its configuration, which is 2-8. Notice it equals what? 10. These are 10 what? Protons, which equal the electrons in an atom, which is neutral. So 2-8 is neon. However, if electron from the second jumps to the third, okay, so if we have an electron that goes from the second, okay, second energy level, okay, goes from here and jumps to the third, this is going to go to a 7 and this will go to a 1, and that's what we see here. So there could have been another choice that was excited, but if it has to be neon and if it was an atom, we know that it had to have the excited configuration of 10, okay, electrons. All right, and of course 2-7-1, which is the choice, had 10 electrons. Just making sure we're aware of that. So 31 is definitely 3. Number 32 is next. Number 32, some information about the two naturally occurring isotopes of gallium is given in the table below. All right, so we have gallium-69, gallium-71, and its actual U, which is atomic mass units, is 68.9, 70.925. Okay, and for these two types of isotopes, notice they're both gallium. The different mass numbers indicate that there's different number of neutrons. That's what isotopes are. Same element, same number of protons, but different number of neutrons. Therefore, the mass is different. Notice the abundance, the percent abundance of these different isotopes in nature. Gallium-69 exists in larger quantities than gallium-71. Okay, so number 32, which numerical setup can be used to calculate the atomic mass? Now, the atomic mass of gallium that we see in the reference table, and let's take a look at that for a second. So gallium here has an atomic mass of 69 point, okay, 723. What does that mean? That means that gallium, when you consider all of its isotopes, notice 31 here. So gallium 31, that's of course its atomic mass. Now they said 71 was one, and it was gallium, that's supposed to be 31 on the bottom. I believe 69 was the other that we had there. Okay, and so if you notice, the 69.7 is an average of both of these. And you say, why do I have to do the problem if we're going to average? Well, this is called a weighted average. So they take all the isotopes of gallium, and using the abundances of nature, the percentages, they do an average to come up with this. And notice this is closer to 70, well, this is like 70, right? It rounds off to 70, okay? And so it's a little closer to 70, okay, than it is 71, so but probably gallium-69 is a little higher in percentages. And that is what we see here. Okay, we see that although it's not 69, it's close to it. The reason why the number was closer to 69 than it was 71 is that this one is in greater percentages. So we have to do an average, but not a straight average. A straight average would make everything that we're averaging have the same percentage worth. Let me explain it this way. Let's say that I have a test average, a lab average, and a quiz average. And let's say that I average a 90 on all my quizzes, and I average an 80 in all of my labs, and let's say I average a 70 on my tests. Now, if I did a straight average of all these three different grades, okay, obviously we would come with the middle number, which would be 80. But what if I weighted the average, meaning that 60% of my class grade is due to tests, 10% is due to quiz grades, and then 30% is lab grades? Well, where's the most of the weight is weighted on the lower end. So our average should be less than 80. If we did a straight average that we did normally done in class, 90 plus 80 plus 70, what you would get is 70 plus 80 plus 90 divide by 3, and you would get 80. But that would be assuming test average, lab average, and quiz averages are exactly the same weight. In this case, since there's only 3 of them, each one would be 33.3%. But that's not the case. So to actually come up with the value would be, given these weights, and now I say weights, but that's also really natural abundances here. So I would take 60% of 70, so take my 70, times it by 0.6, right? Because I'm moving the decimal place 2 places. I'm going to add it. That seems weird, but we're going to add it, okay, to 30% of 80. So 80 times 0.3, same reasoning. Add it to, Okay, 90%, it's really 9, right? 10% of 9, 10% of 9, so 90 times 0.1. And let's put that in our calculator. And you get 75. And you can see that our average is pulled below the 80 because what? 90% of my weight was at 80 or below, right? Only 10% was above 80. Okay, so it makes sense. So that's the reasoning why the atomic mass on the periodic table is closer to this number because of that weight. So how do I do this? Same idea. Do a weighted average. Okay, so we're going to take 60% of 68.29, so 68.29 U, and this uses atomic mass units given in table D, times 60. Move this decimal place 2 places, right? So 0.610, so I like this so far. We're going to add it to 39% of 70, 70.95, and that's good. Move this decimal place 2 places, that's what we have here, and this is the correct answer. Okay, so just a classic weighted average problem. I've seen this in part 1. In part 2, I know I spent time explaining how this works. Okay, it's not a straight average. You're using the weights that are given to you. Okay, do not at any point in times, okay, take this 75 and then divide by 3. That is bad. Don't do that. Okay, take the weights, add them together. All right, so 31 is 1. On to 33. Number 33, a student measures the mass and volume of a sample of copper at room temperature and 101.3 kilopascals. The mass of 49, so we've got a mass of 48.9 grams and a volume of 5.00 cubic centimeters. That's centimeters cubed. All right, the student calculates the density of the sample. What is the percent error? Okay, of the sample. All right, well, the percent error, what we need to know is the density. And density, of course, is equal to mass over volume. We have the mass, it's over the volume, so let's go find that number. Okay, so 48.9 divided by 5, and that gives me 9.78. So my density is 9.78. Now, that of course is gram per centimeters cubed, and that's my density. Okay, now we need to know the percent error of the student's calculations. All right, now they said room temperature and 101 kilopascal, so we need to know the known value of copper. Where could I find that? Table H, let's go there. So here comes table S. Because we need a percent error, we need to know the known amount of density for copper. So I'm going to scroll down and find copper. Copper is Cu, and its density is 8.96, and its units are given to you on top here is grams per centimeters cubed, so 8.96. Let's go back to our work. So the density of copper is 8.96 grams per centimeters cubed. That is the known, or the theoretical. Here is the experimental, because a student measured that. And to do a percent error, we need a formula for percent error. Well, table T is our friend. Let's go. So table T, what we got is percent error, so the measured value, which is the experimental, minus the accepted, or the theoretical that we looked up in a table, divided by the accepted times 100. Let's do it. So using the formula from table T, 9.78 minus the accepted, 8.96, divided by the accepted times 100, put that in your calculator, I get 9.15% error, which rounds to, at least in this case, 9.2, which is choice 3. So a little bit of work there. You had to look up the accepted, you had to calculate the experimental or the measured value, okay, and then of course plug it into the calculations. Obviously you may have known the percent error formula already, but table T is your friend there. And then table S, it's a little good question. Remind yourself that densities, okay, the known densities, okay, are given there in table S. So 33 is choice 3. 34. Number 34. What is the chemical form of sodium sulfate? Now, sulfate is a polyatomic ion. In table E, if you look up sulfate, you will see that it's SO4 -2. You don't have to know that. Table E is your friend here. Okay, it lists all the polyatomic ions. These are clusters of nonmetals that have a charge. And of course, I called table E the what the heck is that table. Now, what the heck is a sulfate? There's a whole bunch of them listed there. But this whole cluster sticks together and is -2. Now, what is sodium? What's the charge of sodium in this salt? Okay, well, it's a group 1 ion, so it would be +1. Again, let's go to the periodic table so you can see these because this information is available to you. If you got this wrong, it's possibly because you got the wrong polyatomic ion. So let's go to table E first. So table E, the polyatomic ions. Okay, so sulfate, there it is, SO4 -2. Notice got a bunch of just weird names here. Generally speaking, okay, if you hear an "ide" at the end of a salt name, it's usually just a what? A singular element. For instance, this is calcium fluoride. Now, calcium is +2, F is -1, but this isn't ID, this is sodium, okay, iodide, all right? Sodium oxide, okay? So notice the IDE tells you it's just a singular element, okay, that is at the end. If you have a group of elements, it's going to have some other name other than I. Now, there are some exceptions to that, but the rest of them, okay, have unique names. Now, let's go to the periodic table to see, because we're doing sodium sulfate. So what charge is a sulfate, is a sodium? Let's go to the periodic table. Okay, sodium, a group 1 ion, it's an alkali metal, and the charge it likes to become is +1, upper right-hand corner. So sodium's +1. So the periodic table told me that sodium likes to become +1. Table E told me that sulfate's -2. And now this is a compound, so therefore it has to be neutral, and it's an ionic compound. So this whole thing here is -2, and this element's +1. So clearly to make a neutral compound, as compounds always are, I need 2 sodiums. So I need a coefficient of 2 to make that +2. And 1 sulfate. And there's where I get Na2SO4, and that's why choice 1 is the right answer. On to number 35. Number 35, given the balanced equation, all right, it's balanced for us, and look at the energy on the product side, screaming exothermic. I know, it's just fun to say that. If 46 grams of sodium and 71 grams of chlorine react completely, my advanced students, if it's reacting completely, both of these are limiting, right? There's exactly the same amount needed, so all of this reacts completely, no excess. What's the total mass of sodium produced? Well, if the total mass of my reactants, okay, is 46 and 71, can anyone guess what the total mass of my products will be? In a chemical reaction, there's conservation of charge, there's conservation of energy, and there's conservation of mass. So if I do my arithmetic correct, I get 117 grams of reactants that completely reacts. Therefore, you're going to make 117 grams of product. That's all that reaction is. Now, could you take 46 grams of sodium and convert that to moles? And of course, you could have. And that'd have been 2 moles. And do the ratio. Well, that's 2 to 2. So whatever moles of this, I get moles of that, and that's 2 moles. Now, what's the formula mass of sodium chloride? Well, if you went to the party, 23 plus 35 is 58. Okay, 0.5 times that by 2, and there's the same number. So you could have done stoichiometry. Okay, you could have done mole ratios and do mole to moles and convert. This would be a stoichiometry, a 3-step problem if you want to start at 46, but this is all this was. There is no advanced stoichiometry problems. The most I have is mole to mole. So in the questions like this on the Regents, this is just a conservation of mass problem. I've seen questions where they gave you the mass of the products, the mass of one of the reactants and they wanted the mass of the missing reactant. And of course, that'd be a subtraction in that case. But that's just all the mass of the reactants have to be the mass of the products. It's all that is. Okay, and there's nothing more to say there. So 35 is choice 2. And I've seen that question in part 2. Part 1, again, the most advanced one, again, this is be 117 grams. The most advanced one is they give you the total mass of the products, and they give you the mass of one of the reactants and say, hey, what's the mass of the reactant that was needed? And that'd be 117 minus 46 to get to 71. That's the most advanced form. And again, you could have done this using stoichiometry by converting 46 grams to moles of sodium. And 1 mole of sodium, by the way, has a mass of 23. That's how I got 2 moles. Okay, or I could have done the same thing here. Chlorine has a mass of 35.4. So 71 is approximately 2 moles of that. Okay, and if I have 2 moles of that, okay, you could see what I can do there, and you could do the mole ratios to get to 17 as well. I don't want to bore you there, but it's simple as just adding numbers together for these types of questions. Conservation of mass, 35 is 2, on to 36. Number 36, given the balanced equation again, well, thank you very much. They balanced it for us. The mole ratio of NO to NO2, careful here, from NO, there's 2 of these, to NO2, to 2 of these. Okay, so a 2 to 2 ratio, reduce it, you get what? A 1 to 1. And that's why choice 1 is the answer. Be careful. They could have been nasty and said the ratio of, let's say, NO2 to O2. And a lot of people would say, oh, there's nothing in front here, so that implies a 1, 1 to 2. And some people would put 1 to 2 if they asked that question, because they like to read left to right. But if it's NO2 to O2, if they change that question, I've seen them do that, in that case it would be 2 to 1. But in this case it was just NO to NO2. And it was a 2 to 2 ratio, which is the same thing as 1 to 1 reduced. Very simple problem. Sorry if you got that wrong, but don't get it wrong again. I've seen that. This another very common Regents question. On to number 37. Number 37. A particle diagram below represents a solid sample of silver. Hello, silver is an atom or atoms of silver. And therefore, by saying silver, I represent them silver atoms to be an atom. And as we know, atoms, you say neutral. These guys are neutral, which means their protons equal electrons. So this electron must be its valence electron that belongs to silver rest of this. Now, these valence electrons of silver are loosely held. As you can see, every silver doesn't have an E close to it. And so hopefully you can recognize that we are in some kind of arrangement, aren't we? These silver ions are in some kind of organized pattern in a crystal lattice. That's why they're solid. That's why silver is solid. And so what keeps these silvers together is that each silver is attracted to all the other electrons from all the other what? Silvers. And they're loosely held. Notice this silver doesn't seem to have an electron, or whose electrons do they belong to? As we learned, there's a type of bonding where we have metals who have loosely held electrons, and they're in a sea of mobile electrons that are able to move throughout the crystal. So this sea, and I'm going to write it because it's an important catchphrase, it's a sea of mobile electrons. And what that means is there's mobility of these charges, great conductor of electricity and heat, and there's a crystal pattern. So these are metals bonded to each other. These metals are bonded to each other in a sea of mobile electrons, and that screams metallic bonding. That's how solid transitional elements or metals that are not transitional love to bond with each other. They have these loosely held electrons, and every positive core of silver ions, okay, can basically attract everyone else's electrons. All these atoms or all these ions that have the core electrons are attracted to everyone else's moving mobile electrons. So all of these ions of these atoms are attracted in all directions of all the electrons, and their electrons are able to move because they're held loosely. And that's reason why you can bend, twist, and heat these guys and shape them into any shape, and that's why they call it malleability. It's a property of metals because of this bonding. Another property, you can actually pull these guys to be very, very thin because of this type of bonding. Think about it. These ions can attract in all directions, so they can be twisted into a very, very small little wire. It's called ductility. And of course, because of the mobile charges, okay, they're great conductors of heat and electricity, and that's exactly what metallic bonding is. Metals bonded to metals. Okay, hydrogen bonding is an attractive force between electron deficient H's. Okay, covalent bonding is metal and nonmetal. Ionic, for the most part, is metal and nonmetal with a transfer electrons. Okay, so this is showing that C of mobile electrons, 37, is 1. Number 38, given the formula representing a molecule, this one, which statement explains why the molecule is nonpolar? We're not talking about bonds, we're talking about the molecule. When you hear polar and nonpolar, am I talking about the polarity between the bonds or the entire molecule? In this case, the entire molecule. So if you think about a polar molecule, this entire molecule's got electrons, it's got protons in different areas. But does one side have any different than another side? Is there a side with more electrons than another? And we would say because of symmetry, okay, there's the same type of carbon to hydrogen bonds in all direction. There is no side to this that's different from another. So therefore, this is a nonpolar molecule. Now, just so you understand, we would call these polar bonds because there are two different nonmetals who have two different electronegativities who will share a little bit unequally in this course. So we would say, in terms of the molecule, we're not going to talk about electrons are shared between carbon atoms and hydrogen atoms. This would be talking about the bonds. Transfer of electrons would mean that we're talking about an ionic compound. For instance, if I had sodium atom who had one valence electron and chlorine who has 7, and because chlorine is more electronegative, would pull this electron away and become -1. And this one would lose that outermost and become positive, and that's how ions are formed. That'd be a transfer for an ionic compound. We're not talking about that here. We're talking about that the distribution of charge is equal throughout because of symmetry. So for a symmetrical molecule, everything's the same all the way around. There's no one side different than another. Being polar means you have differences. There is no difference here because of the symmetry. And that's why 3, okay, for 38 is the best answer. If there was an asymmetrical distribution of charge, then we would be a polar molecule. Case in point, if this is a molecule containing all of the atoms, and there is more electrons on one side than another, then we would call this the negative pole, and this side that doesn't have as many electrons be the positive, and this would be an asymmetrical distribution of charge. Okay, all right, and that's important when we talk about that. Here, the distribution of electrons is equal throughout, so there's no difference because of the symmetry. All right, and that's why 38 is 3. On to 39. Number 39. A solid sample of a compound and a liquid sample of the same compound are tested for electrical conductivity. So we've got a compound, and being a compound means it has a distinct chemical formula. So we have the same compound, and this compound's in the liquid state, okay, and then also in the solid state. And we tested them for electrical conductivity. Which test conclusion indicates this compound is ionic? Now, first of all, to be ionic would mean that we have a positive ion attracting a negative ion, okay? And in truth, because these attractions are very strong, This positive, who is positive on all direction, could attract another negative. This could attract another positive, and what we have is a crystal lattice. This would be a positive on this side, this would be a negative, and these positives and negatives would grow in all directions and make a crystal lattice or a regular repeating arrangement, kind of like what we see in this box here. That's for another question. Now, in order to conduct electricity, in order to have conduction of charge, okay, we need two things in chemistry. Number one, either free mobile electrons, which we have in metallic bonding in that diagram of silver below. We know silver or metals are great conductors by themselves in metallic bonding because they have a sea of mobile electrical charges, electrons, that are able to move throughout the crystal. So you either have that, or if you don't have free mobile electrons, and ionic compounds do not, they lost their valence or gain their or filled their octets by losing or gaining electrons. So they don't have any valence electrons. They're just positive or negative. But you have to have free ions. So you either have free mobile electrons or free ions to conduct electricity. So ionic compounds, because positive and negative attract each other so strongly, okay, solid ionic compounds do not have free ions. They do not have free mobile electrons either. So therefore, solid ionic compounds never conduct electricity because these ions are in a fixed position. The only way the solid could conduct if these ions could move throughout the crystal, but they cannot because they're surrounded by other negatives. Like another negative ion would be here, and there would be one above it and below it. So solid do not. However, if you take this solid and you add heat and you liquefy it so that these ions are free to move, we call this molten, okay, then you can conduct electricity. So to be an ionic compound, one of the major properties that come up is that you conduct in a liquid, okay, or aqueous state, because aqueous means that the ions are free as well in water, but do not in the solid. So both the solid and liquid are good conductors. No, the solid does not have free moving ions. Both the solid and liquid are poor. No, the liquid would be great because it have free ions. The solid's a good conductor. No, it is not, because it does not have free ions. And four, the solid's a poor conductor. True. Ions are locked in a crystal lattice, but the liquid's a good conductor because the liquid has free mobile ions. So that's why choice 4 is the answer. And I'm really going over these questions. So you can see this in part 2. They can say to you, explain why the liquid is a good conductor for an ionic compound while a solid is not. And you would say the liquid has free mobile ions, and that'd be the key to the problem. 39 is 4. On to 40. So number 40, which statement explains why 10 milliliters of a 0.5 molar H in front, that's an acid, okay, neutralizes, that's a key word that we use in acid-base reaction, okay, of a base. So they're trying to say, why does this amount of this concentration of this acid, which by the way is given to you, okay, in table L, and this base is given to you in table K. So these guys are given to you as acids and bases. And what is neutralization? Neutralization is where the proton from the acid plus the hydroxide from the base come together and make water. Acids or protons themselves, okay, are very acidic and are corrosive. Hydroxides themselves are called caustic, and they equally can break down organic matter on high concentrations. In fact, liquid Drano eats through clogs in your sink by adding sodium hydroxide, a strong base. Strong acids can eat through flesh, okay, if the acids are strong enough. So these guys by themselves are dangerous, and we can neutralize. And that word neutralize means we can make a neutral what? Compound or a neutral pH. A pH of 7 is pure water if one H plus hooks up with one hydroxide. So neutralization, if we're going to exactly neutralize, that would mean all of the H pluses from the acid, right? The acid produces the H plus. That's the Arrhenius definition. And the Arrhenius base definition is all the hydroxide from the base. So the H plus the hydroxide, okay? So it's just the number of H pluses has to match the hydroxides. That's what neutralization is. So the best answer here is the moles, which is just a word that describes how many, of H plus equals the moles of hydroxide. And 1 is the best answer and exactly neutralizes. Okay? You can't say the moles of the acid equals the moles of the base because this acid is what? Diprotic. It gives off twice the number of H pluses. So you can't match the same number of these molecules. You'll have more H pluses than hydroxides. Okay, and the moles of H2 are greater than the moles. That's not exactly what neutralization. Neutralization is about the protons matching. Okay, if you want to do it mathematical, you can, because to get the moles of H2SO4, you can take the 10 milliliters and you could do the MV equals MV and see if it works out. MV of the acid should equal MV of the base. All right, but you don't have to do any math here. The bottom line is exactly neutralizer and matching all of this. And we've seen this before, okay, because we've seen this in different ways in this test. For instance, we've talked about that there has to be conservation of mass, one H for one and one OH. So we have two H's all together on this side, right? So there's an H and there's an H, and therefore we have two H's, and then we have what? One O. So we have conservation of mass. We have conservation of charge. Hello, H plus and a negative. That's 0 on this side, 0 on that side. If we could measure the energy, there's conservation of energy as well. So when we did a problem back, I forget what number it was, but we know that in redox reactions, we know that the number of electrons that are absorbed and therefore reduced is equal to the number of electrons that are oxidized. Okay, so electrons that are reduced are the same number of electrons that are oxidized always. And the same thing happens with acid and base, except we're not dealing with electrons being accepted or passed around. We're talking about protons and hydroxides here. So we're just matching the H pluses with the hydroxides, and that's why 40 is 1. On to 42. On to 41. 41. Which particle diagram represents one substance in the gas phase? We know gases because they fly around their container and bounce around hundreds of miles an hour are always going to fill their container. So clearly a gas phase would meaning they always fill their container. And so 1 and 3 are the best choices, whereas 2 and 4 looks like a regular repeating geometric pattern. These are solids. Okay, they have definitely some arrangement. Liquids would not be as organized, and liquids won't always fill the container. So 2 and 4 are gone. Now we have to know a little bit about our classification of matter. What's a substance? A substance is either equal to an element, which is either the same element bonded to themselves, diatomic, this could be hydrogen, or it could be a compound, two or more different substances like HCl. So if you notice, this would actually be a mixture of two substances, two elements. And we're not talking about a mixture, we just want one substance, and therefore 3 is the answer. Number 41 is 3. Okay, number 42. Given the equation representing a chemical reaction at equilibrium in a sealed rigid container. Okay, equilibrium, double arrows, the rate of the forward equals the rate of the reverse. When the concentration of H2 is increased by adding more hydrogen gas to the container. When the concentration of H2 is increased by adding more hydrogen at constant temperature, the equilibrium shifts how? Okay, so I like to teach this with stress and response. Okay, so when the concentration of H2 is increased by adding more hydrogen gas, so we're going to add more hydrogen gas than we're supposed to have at equilibrium. That's going to be our stress. That's what we're doing to. We're going to increase the hydrogen. Now this is Le Chatelier's principal problem. I love drawing this diagram because it really helps students see what's really happening, because arrows are we're increasing one, but then it decreases. It gets confusing. Stress is what we do. This is what the people do. We do this to a reaction that's already at equilibrium. It's already balanced. Balanced in the sense that the amount of these guys are staying the same because their rate of the forward equals their rate of the reverse. That's the balance. We're going to upset that balance by adding more H2 than I'm supposed to have at equilibrium. Okay, now the response is what the reaction does. This is what the reaction does to regain its balance. Okay, it's important you get that. So we increased H2. Now we have more than we're supposed to. It's out of balance. When there's more than you're supposed to, the only way to correct it is to lower. So the response is always going to be opposite. And Le Chatelier's principle states that a reaction equilibrium will undo the stress to regain its balance. And to undo it, it's going to do the opposite of its stress. And it's going to shift left or right, meaning instead of equaling the rate of the forward equals the rate of reverse, one of the rates is now going to be faster than another in order to regain that balance. And the best way to explain that is if a person, and this would be me with all this blue hair, and you push on me this way, I would fall over unless I push back with my feet in the reverse. So this is the stress by me pushing on, or someone pushing on me. It's the stress on me. And my response is going to do the opposite by shifting in the other direction to relieve that stress or to prevent myself from falling down. The reaction prevents itself from uh, ever getting out of equilibrium, so it basically shifts in the direction to regain its balance. And it does so by shifting to undo what was done to it. We did the stress, the reaction is going to shift in response. So if I add more H2, this reaction is going to shift. One of the, either the forward or reverse is now going to be faster to lower H2. It has to lower H2 to regain its balance. There's too much H2 than it's supposed to have. So it has to lower it. Now think with me. Either I'm going to shift this way, it's left or right, or I shift in the reverse. Now, if I shift in the forward, that means I'm going to use up HI to make more I2 and H2. Whoa, whoa, whoa. The response is I have to lower it. So that doesn't make much sense. So this top shift, okay, doesn't make any sense here. So let's get rid of that one as well. Okay, so it makes sense in order to regain my balance because there was too much H2 that was added, we're going to shift to the right. And that means that we're going to increase HI because H2 and I negative are going to get used up. If the forward reaction now is faster than reverse, that's what the shift means. We're going to use up. We always shift, okay, in the direction of what we're going to make more of and shift away from what we're going to lower. And that's what's happening here. So we would shift to the right. And in that way, shifting to the right, that's the response. The reaction lowers the H2 to regain its balance. And the concentration of HI has to increase. If we're going faster in the forward to use up the H2, the HI has to increase. And by the way, these guys are on the same team. So if you're shifting to the right, both of these have to get used up together. So therefore, 2 is the best answer. We applied a stress, too much H2. The reaction responded by shifting to lower H2. The only way to lower H2 is to shift away from it so that we use it up, arrows going down, to make more of that product. And that's why 42 is choice 2. Number 43. Which diagram represents the potential energy changes during an exothermic reaction? Exothermic means like, hey, we've got, let's say, hydrogen plus oxygen, and this is a balanced equation. Gives me 2 water molecules, and there's heat, there's energy that's exiting, that's produced. Remember, this is the reactant side, this is the product side, and if heat is on the product side, that means heat's being released and exiting. Now, where does energy come from? Well, it came from the potential energy that was stored in the chemical bonds here. So this would be a heating curve. This would be a proportionate, like, pressure temperature kind of a relationship. But a chemical reaction, we either have endo or exo. Now, for exothermic, we have something that's unstable, okay, high energy, and then we produce something stable with low energy. And the difference of where you start and finish is that delta H, which in this case is the energy that's released. We have all this energy. This is the potential energy of the reactants, which would be this right here. This is the potential, and this little line right here is the potential energy of my products, a lot less. The reactants had all this potential energy. The products have a lot less. What happened to it? It got released. So therefore, okay, the exothermic reaction is choice 4. Okay, in the reverse, we start with low potential energy of my reactants, and we start with what? High potential energy of the products. How'd that happen? Well, the difference of where you start and you finish, that's delta H, that's right here. In this case, it's positive because it's going up. Why is it going up? Because we had to add energy to start low to go high, and this would be endothermic. That's if the heat was on the reactant side. So this delta H would actually be negative because it's going down. It's starting high and going down, and it goes down because the energy was released. Exiting exothermic, choice 4 is the correct potential energy curve, okay, for an exothermic reaction. Choices 1 and choices 2 are not potential energy curves, although there's potential energy in a heating curve. That's not what they're talking about here. Okay, so that was choice 4 for 43. On to 44. Which compound, number 44, which compound is classified as an ether? Now, if we go to table R, you'll see that an ether, and I like to think of on either side, okay, is given this R to O to R prime. In fact, in table R, they give you an example. They give you this example, CH3, CH2, O, CH2, CH3. And this is a 2-carbon group from table P is an ethyl. So this would be diethyl ether. But doesn't matter the name. You just need a rest of an organic compound, hey, and then the rest of another one. That's R prime with an O in the middle. So the question is, where is that? Well, 2 O's is not what we have here. That would be an ester. Okay, so this could be it, or this one. This O is it at the end, and this CHO is a CHO-MAMA group. That's an aldehyde. I always tell you that CHO-MAMA groups are aldehydes. Okay, and so the O in the middle, this is an O at the end. It's either this one or this one. Let's take a look at 3 for a second. Let's do the structural formula because it gets kind of confusing. We have a carbon, hydrogen, hydrogen, hydrogen. Then we've got a carbon. If I bond it to an O, like it suggests, and then go CH3, I have some issues here because carbon must make 1, 2, 3, 4 bonds, and this carbon is 1, 2, 3, 4, but this carbon only have 1, 2. Now, if I make a double bond here with the O, I still need an extra bond somewhere, and there's no extra bonds. The only way to explain this is that I have a CH3. This carbon must be double bonded to an O, then the CH3. And my friends, in table R, this is what a ketone looks like. So that's not an ether. If you look at this one, this would be CH3 bonded to an O. Notice the CH3 on the other side. And that makes sense. Every carbon is bonded to 4, and I have this general formula of O's in between hydrocarbons. You say, Mr. Grodsky, I have a hydrocarbon between these O's, but this is a carbon double bonded to the O. The only way to explain this structure right here with a C and an O is a carbon double bonded to the O. If you look at choice 4, you've got that scenario here. This is a C double bonded to an O. The only way to explain a C by itself like that. And then you have the CH3, and this is an ether. So a carbon double bond to the O would be a C and the O sitting there. Notice there's no C by itself with an O. So 2 is the ether. Table R is your friend. I got this general formula. The only little tricky part was understanding that the O's in the middle, this C, The only way to explain this C to O would mean it'd have to be double bonded to a ketone here. So that only two choices, but the O in the middle that's correct is choice 2 because of that. So 44 is choice 2, on to 45. Number 45, given the equation representing a reversible reaction, A equilibrium, rate of the forward equals the rate of the reverse, therefore the amount of these guys are constant, which formula represents the H plus acceptor? That's from the other definition. An H plus acceptor from the other definition, they don't call it by name. Arrhenius said to be a base, you produce OH minuses, okay? But here, you're a base by being an H plus acceptor. Now, not asking for that, but just saying which in the forward direction is accepting an H plus. Okay, well, let's see what we got here. HCO3 negative, this is the bicarb ion or hydrogen carbonate, in the future becomes H2CO3. Look at that for a second. In the future, this guy has one more. How'd that happen? How can HCO3 grab an H plus? Notice it was a negative charge, and notice in the future, which going in the forward, it has one more H and there's no more charge, because if I add a positive to this, it becomes neutral. Now, so clearly this one had to accept an H, and therefore hydrogen must have given this guy a proton. And to make sense with that, H2O, if it gave off a proton, should have one less in the future in the forward direction, and it does. So it makes sense that HCO3 negative, okay, was the H plus acceptor, choice 1. Now they could have said in this question, in the forward direction, which one is the base, without doing all of this nice stuff telling who the H plus acceptor was. Now, so to remember the H plus acceptor is the base, remember the opposite. The H plus donor must be the what? The acid. Acids give off H plus. That's a donor. My gosh, that's terrible. Okay, so the H plus donor is the acid only, is the acid definition, because guess what? HCl, okay, gives off H pluses. That's Arrhenius. But the other definition means that which is the Bronson-Lowry, but we don't use it by name because I guess they figured you can't handle it. Okay, so the point is that this gives off H plus to actually other things. Okay, so the water is acting as the acid, and the bicarb is acting as the base. This is donating, this is accepting. 45 is 1, on to 46. Number 46. What is the mass of an original 5.6 gram sample of iron 53 that remains unchanged after 25.53 minutes? Party people, know where you are on the test. 1 through 30 goes through the entire curriculum, and then 31 through 50 does the same thing. So we're toward the end of the curriculum. We're in nuclear chemistry. Notice we just did organic chemistry in 44. We did some acid and base. Okay, looks like we skipped redox in this part, but looks like we're in, now we're hitting nuclear chemistry. Okay, nuclear chemistry kind of hits at the end of each of these segments, 1 through 30 and then 31 through 50. So this is a half-life question. Now with a half-life question, I always teach my students to do a 0 line. This is 0 half-lives have occurred. There's 100% of the sample, and 0 time has occurred. Now what they said was, we had an original 5.6 sample, and the total time that occurred from the 0 timeline is 25.3. They want to know how much of this sample remains. Now it's going to have every half-life to some value. In order to know how much remains, because iron 53 is radioactive, because table N is going to help me identify its half-life. So iron 53, let's look it up. Now what's iron 53? It's an isotope, a radioisotope. It's a wrong number of neutrons for iron. And so let's go find table N and see what the half-life of this is, so that we can finish this problem. Because once we know the time it takes for it to halve, we can figure out how many halvings, and then we can just have this that many times to see what remains. Let's go to table N. So here we are with table N in all of its glory, and it gives me the nucleotides of selected isotopes that are radioactive, that give off certain decay mode, but we're after the half-life of iron 53, which is 8.51 minutes. That's the time it takes for half of an original substance to decay into something else. It's a positron decay, so really it has two less neutrons, so it's fixing itself that way. It's an unstable nucleus getting stable, okay? But the bottom line, we're after 8.51 minutes. That's the number we need to answer the question or continue on with the question. So let's go back. Okay, so we found out from table N 8.51 minutes, okay, was the time it takes for a sample of iron 53 to decay in half its mass to change to another nucleotide, to another element, naturally transmutate. Okay, that's what half-life is. So you notice I put that divided by 25.3, that's a total time. I want to figure out how many halvings have occurred. This is the time it takes for one halving. This is 25.3, the total time. So I'm going to take my 25.3 and I'm going to divide it by my half-life, which I got from table N. Okay, so I get 2.97, so 25 divided by 3, that equals approximately 3 half-lives. 2.97, I'm going to round to whole numbers. And these types of math problems, these half-life problems, always round to whole half-lives. Okay, so 3 halvings have occurred. 1, 2, 3. Now I know that 5.6 is the first one. So you take your 5.6 and let's go do the first half-life. So 5.6 divided by 2 and you get 2.8. Wherever my, so 2.8 is how much remains. Now we're going to do the second half-life. Half of this, well, that's 1.4. And the third half-life is going to be 0.7. And that is our answer. Okay? So we found out that 3 halvings have occurred. Now they could have set this problem up another way and said, hey, what fraction of the original sample remains? Remember, the first half-life is 1/2 of the original. The second half-life is a half of a half, which is 1/4. The third half-life is a half of a fourth, and that's 1/8. So they could have said what fraction remains after this time, and you could have said 1/8. But we figured out that 3 halvings have occurred because we needed this number, okay, from table N. And then we divided to get the total number of halvings that occurred, and then we halved going down. So you understand, they could have given you also another twist to this problem. They could have given you that 0.7 remains and not give you this number here and say the same problem, how much of the original sample did you start with? And so you take your 0.7, do the same problem, say 3 halvings have occurred, and you would what? Double up 3 times. Okay, so I'm just giving you all the different ways that you can see this same problem. So that's number 46 is on to 47. Number 47, given the equation representing a nuclear reaction, again, we're in nuclear chemistry area of the test. Okay, the particle X is represented by. Okay, so when we do a nuclear equation, these are basically we care about how the nucleus changes. That's what a nuclear reaction is. And a nuclear reaction has mass and it has, of course, protons on the bottom, or the charge, however you want to think about it. But what do I do know is that 6 plus 4, all the top numbers on one side of a nuclear equation have to equal all the top numbers on the other. So 6 plus 4 is 10. So we have a 1 by this H, or this proton here. So 1 plus 1 equals 10. So 1 plus what number equals 10? Remember, you put equal signs on equal sides of the arrow, or the other side of the arrow. So 6 plus 4 is 10. We have to have 10 on this side. We already have a 1. So what plus 1 equals 10? Obviously, that'll be a 9. Okay? Now, we have 2 choices with a 9, so we're good, and these guys we can toss. Now, same thing on the bottom. All the numbers on the bottom of one side have to equal all the numbers on the bottom of the other side. Very simple, okay? And you would say, well, is that a conservation of mass? Sort of. There's a mass defect here in nuclear crisis. Here in these types of problems, although we're coming out with the numbers, there's truly some little tiny missing mass, but we'll get back to that another day. So in any case, 3 plus 2 is 5. So what number plus 1 is 5 and 4? So 9 over 4. Now they're both 9 over 4, and this is the biggest mistake people make when they do this question in part 2. They'll put 9 over 4 and they'll put the wrong element. Who is atomic number 4? We need the right symbol for atomic number 4. Remember, atomic number is the proton number, and proton numbers identify the elements. So you've got to go, okay, to the periodic table. Let's go there. So the element that's atomic number 4, okay, is beryllium. So 47 is choice 2, okay? And again, as I'm a broken record, these types of reactions, okay, these types of problems are also in part 2. I've seen part 2s where they gave this reaction, say, hey, fill it out, and they would just leave this blank, and you'd have to give out the right numbers on top and the right chemical symbol. Number 48. Number 48, fission and fusion reactions both release energy. In fact, they release more energy than any other type of reaction. In fact, chemical reactions don't release anywhere near the reactions of these atomic. Nuclear reactions give off far more energy than chemical reactions. You've got to get that down. Now, what they're doing, and I bet if you got this wrong, you confused fission versus fusion. Fission is splitting the atom. Okay, and so fission requires large atomic number atoms like uranium to be, or plutonium, to be split into smaller, more stable fragments. You should have learned that atoms that are huge number of protons beyond atomic number 83 are unstable because they're just can't hold that many protons. That nucleus is just overstuffed, and those protons are repelling themselves, and it's just an unstable scenario where they want to change themselves. So large atomic nuclei are primed to be split into smaller atoms that are more stable. Things are thermodynamically go from unstable to stable. So this is describing fission, okay? Create radioactive products. Yes, fission can do that. Okay, it can create anything, any type of a sequence of particles that are slower, and it can definitely make some radioactive particles. Okay, fusion does not. And of course, we're using radioactive elements mainly because they have an overcrowded nucleus that makes them unstable. So the only one that makes sense that explains fusion, and fusion is when we take a heavy hydrogen, okay, and another heavier hydrogen called a tritium sometimes, and we put these together, and what we get is we get a helium nucleus because all the numbers in the bottom, and we get a 4, and then we get a 1 and a neutron and a 0. Here's one case where we're using light nuclei. They're fusing. They're coming together. And that's one way to remember what fusion is. Okay, so 48 is 4. Okay, on to 49. Okay, 49, we have white and black forms of phosphorus. Hey, they're all phosphorus. They're same number of what? Protons. They just have a different structure if they have different properties. If they have different colors, therefore their structure is different. They're all made from the same type of atom, kind of like diamonds and graphite. Graphite's on the tip of your pencil, and diamonds, of course, you should know what it looks like. It's on, you put them on rings or jewelry, and you would never put the tip of a pencil and switch them. You can't write with a diamond, and I would never, I hope not, okay, display a graphite ring, although it might be cool in some aspects. And the reason why carbon and graphite, or graphite and diamond, both made of carbon, have different properties is because they have different structures. I can't say this enough. Structure is king. You change the structure, you change the properties. So these guys have different structures. Which phrase describes the two forms of phosphorus? Same crystal structure. No, look at the structures. The crystal shape is not the same. Okay, they have different crystal structures, and therefore, because their structure is different, they have different properties. Okay, so that's all I got. So again, this is pounded into you. Structure is king. Change the structure, you change the properties. Melting point and the color of these are physical properties. Okay, and you change the physical and the chemical. In this case, the physical structure is king. Different structures, different properties. It's listed right there. So even if you didn't know structure is king, you should be able to deduce that by the information given. Number 49 is 3. On to 50, and the last multiple choice question. So number 50. Which graph shows the relationship between pressure and Kelvin temperature for an ideal gas at constant volume? Okay, so as temperature increases, absolute temperature, molecules go faster, right? Temperature is the average motion, is the average kinetic energy, kinetic is motion. So you give them more temperature. If their temperature increases, they're moving faster. If they're moving faster and the volume that these guys are in, I guess they're in some sort of rhombus or trapezoid, or I should just say parallelogram. I can do this, okay? Any case, if they're in this kind of container, okay, and it's a constant volume, and I make them all the gases go faster, they're gonna collide with the container wall more. And the collisions, if you've increased the collisions and the smacking of these molecules, you're gonna have a greater force over the same area, which is pressure. Each collision will be stronger and there'll be more of them, so there'll be a greater force on this container. Hopefully the container can take it and doesn't explode. Hello, throw an aerosol can into a fire, or you throw something under pressure and heat it too much, it can explode. So as temperature increases, so does pressure. And this is a direct proportion, and this is the best answer, okay? Don't fall for choice, okay, 4, which would be pressure volume. That'd be an inverse relationship. This is a direct proportion, especially if the Kelvin temperature, okay, and that's all there is to it. Can you understand that temperature is the average motion? Can you increase that motion in it keeping two things constant, number of molecules constant and the container constant? If this container was expandable, we wouldn't have this problem, but because it stays constant, we make these guys go faster, they're going to collide more often, and the force over area, which is pressure, is going to increase. All right, and the pressure increases as much as the temperature. All right, so therefore 50 is 1. And that concludes the multiple choice section. That's called Part A and Part B1, which were supposedly a little more difficult multiple choice questions. You can tell me if they were or not. All right, and we're on to the free response. But as we go on to the free response, and I will have a link at the bottom of this, at the end of this video for that free response video to go through those questions, understand that everything that we went through here as a multiple choice is fair game for the Part 2. That's why I spent the extra time. All right, see you in Part 2.